Okay, can you see my screen?
Perfect.
All right. Okay, so I'm ready to start.
Mm-hmm. Okay, so
We'll look at the chat here.
let's start.
Okay, should I go?
Yeah, maybe I introduce you and maybe talk about a little bit about the day. So, good morning, everyone. Welcome to this second day of the summer school. Today will be a longer day. We will have this lecture, the labs as usual, and then later on another lecture that goes from 5 to 8:30 p.m. So I hope that you don't get too tired, okay? So moving on to the first lecture, presented by André Martins. It's a great pleasure to introduce you. André Martins is currently an associate professor at Instituto Superior Técnico. He's also a senior researcher at the Instituto of Telecomunicações, vice president of AI research at Embabel, a startup company that is based here in Lisbon. He's a well-known researcher on natural language processing, machine learning, has many published papers, and above all, is one of the founders of LXMLS, and is organizing it for like 11 years. And is going to present you linear learners. I hope you enjoy it. André, the mic is yours.
All right. Okay, good morning, everyone. It's also a big pleasure for me to be here. Less of a pleasure because it's not presential, but hopefully next year it will. So today I'm going to talk about linear classifiers. And the first question that we should ask is, why do you need a lecture on linear classifiers? So after all, you are in 2021, everybody's using neural networks right now. Why do you need this? And there's actually a few reasons why we think this is a good idea. First of all, there's many general machine learning concepts that are the same for linear classifiers and neural networks. So the goal of this lecture is to present those. The theory, both regarding statistics and optimization, are much better understood for linear classifiers than for neural networks. So the goal of this lecture is also to introduce some of those concepts. Other than that, linear classifiers actually are still widely used in industry, and they are very effective, in particular when you don't have abundant data. So when data is scarce, or when you have knowledge about how to design good features to solve a problem. And finally, linear classifiers are actually a component of neural networks. Okay, so if you know a little bit about neural networks, just take this simple example. This is a neural network to recognize objects in images. So the goal is to distinguish between dogs and cats. And there are several layers. This is a multi-layer perceptron. We are going to learn more about this tomorrow. And so neural networks can learn these internal representations in their neurons. But if you forget about all layers and just focus on the last layer, the last layer actually acts as a linear classifier. Okay, so the representations that appear here in the last layer to be converted into a probability for the classes, this is an instance of a linear classifier. The nonlinearities are in the layers before that one. And so what we are going to talk about today is to just focus on what you could imagine to be the last layer of a neural network. And actually, instead of a neural network, instead of learning these internal representations, we could imagine that there is some engineer that is handcrafting features for us. So instead of learning these features from data, someone might be just handcrafting them. And what we're going to talk today is precisely about what we can do with this last layer. So here's a quick roadmap for today. We are going to talk first about linear regression. Then we are going to jump to classification, binary and multiclass. We're going to talk about some well-known linear classifiers like the Perceptron algorithm, the naive Bayes model, logistic regression, SVMs. Then in the second part, we're going to talk a little bit about softmax and Sparsemax, and a little bit on regularization and optimization, stochastic gradient descent. And we will end, if time permits, we'll end by talking a little bit about similarity-based classifiers and kernel methods. All right, so let's start by giving some example tasks. You know, an example of a binary task is detecting spam. Okay, so in this case, the input is text, it's the email, and the goal is to classify it in one of two classes. Either this email is spam or it's not spam. So there are two labels. This is why this is called a binary classification problem. Another example is a multi-class classification problem. So for example, we could be given a news article like this one about AlphaGo beating a Go human champion. And the goal is to classify the topic of this article, you know, among a predefined list of topics. For example, politics, sports, technologies, and so on. So in this case, there's more than two labels. This is why we call it a multi-class classification problem. What's happening here? Okay, so this is the outline of the first part. So the first thing I will start is with this disclaimer. You know, some of the slides that I'm going to use in this initial parts are adapted from Ryan McDonald. He taught this lecture a few years ago. And this first simple example came from his slides. Okay, so let's start very, very simple, you know, with a very toy example. Let's assume that our training set is really small. And it consists of input sequences that we don't know anything about. Okay, so this is just, the inputs are just a sequence of symbols, you know, and I'm not telling anything about what these symbols mean. The only thing that we get to see is these sequences together with their label. This is our supervision. This is the data that we get at training time. And so given these four examples, we want to build models that are able to generalize this to new examples to be presented at test time. So let's assume that at test time we got this sequence, and we need to infer what the label should be. Can anyone guess? Maybe using the chat, can anyone guess what is the correct label for this example? Okay, -1. That was very easy. So, you know, this example is exactly the same as example 1. So we are just repeating something that we already saw at training time. So even if you just memorize the data, our best guess would be just to use the same label that we observed at training time. So this is probably the best thing that we should do. What about this new sequence? -1 as well. All right. Yeah. So here it's a little bit more complex because this example is new. But if you look at the training examples, you know, this is quite similar to the first example. It also has an asterisk and a diamond. And the second example is also similar. There's also this art symbol and the asterisk. And the examples with label +1 they seem to be less similar. So our best guess is probably going to be -1. What about this one? Okay, a lot of people are saying +1. 0. Right. You know, somehow there is a bias preferring +1, but I would argue that this is a lot harder. Okay, so why is that? Because on the one hand, you know, asterisks and circles, they occur with labels -1, for example, with the first example. The second example has a triangle and an asterisk, but on the other hand, the third example also has the asterisk and the triangle, and the fourth example has a triangle and a circle. So it's hard to tell which one is the best label. We need to understand a little bit more about the task and about the function that maps from sequences to labels in order to come up with a good answer. So I will keep this one open, but let's ask the question about why can we do this? You know, why could we do it, for example, in the second sequence? And you know, one way of doing this, and maybe this is what we are thinking when we are making these predictions, is we can count how often each of these symbols occur with the labels, and try to infer the probability of the labels given the symbols based on that. There might be some additional assumptions that we need to make. So for example, it really simplifies our life if we assume that symbols can occur in any order. If order doesn't matter, then we just need to count how often symbols occur with each label, estimate probabilities from it, and then make decisions. So for the second sequence, where the label that most of you agreed on was -1, then we can see that asterisks occur more often with label -1 than with label +1. Then diamonds occur equally in both cases, and hearts occur more frequently with the label -1. So there's all symbols occur either as frequently or more frequently with label -1 than +1. So this should make label -1 more likely. For the last example, the one that was harder, if we do the same exercise, we'll get to a tie, right? So we see that asterisks occur more frequently in label -1, but triangles occur more frequently in label +1. So unless you make any additional assumptions, like assuming that the order is important or something like that, it's really hard to make a good guess here. And this was a very simple example, but it kind of illustrates the point. So in machine learning, there's a few steps that you need to make, that you need to take in order to solve a problem. So first, we need to define a model of interest. We need to make some assumptions, and usually we need to make those assumptions. In this case, the assumption is that the order doesn't matter. And finally, we need to fit the model to the data. So as we have a model and a family of models that we can use, then we need to fit the model in this family to the data that we observe at training time. And for this particular example, our model says that a sequence is just a bag of symbols. So the probability of a label given a sequence is the same thing as the probability of a label given this bag of symbols. And if you want to predict the most likely label, we want to maximize the probability of label given sequence. And this will give us a prediction at test time. And the second assumption, or the actual assumption that we are making, is that it's called the naive Bayes assumption, which we are going to talk about later, which says that symbols are conditionally independent given the label. Okay, so this tells us that there is no there is no dependency between the symbols if given that we observe the label. Okay, so this allows us to write the probability of a sequence given a label as a product of probabilities. And as we make this assumption, then to fit the model to the data, we just need to count and normalize. And we'll see that this corresponds to maximum likelihood estimates in this naive Bayes model. Okay, so don't worry if these concepts are new to you. I'm going to come back to naive Bayes and how to fit models to the data in this sort of models. This was more like an illustration. So let me introduce some notation that I'm going to use throughout this talk. So we are going to assume that our inputs are going to be denoted by the letter X. So X could be something like a news article or a sentence or an image. This is the objects that we want to classify. And we are going to denote outputs by Y. Okay, so these are the labels. It can be binary labels like spam or not spam. It could be more than 2 labels, for example, a topic for a news document. It could also be a structured, some structure like a parse tree, an image segmentation, or something more complex. And often we talk about input-output pairs. This is just picking one object together with its label. So for example, a news article together with a topic, a sentence together with its parse tree, or an image partitions into segmentation topics. And I'm using this calligraphic X and calligraphic Y to denote the space where the inputs and outputs live. All right. Okay, so we are going to stick with supervised machine learning today. So this means that at training time, we are given a labeled data set of input and output pairs. Okay, so our training set consists of these pairs that I'm denoting by xn, yn. Okay, and we have n of them. And our labeled data set, I'm denoting it by this calligraphic D. And given these labeled data sets, our goal is to learn a predictor that generalizes well to arbitrary inputs. And the predictor is just a function that maps from our input space to our output space. Okay, so this is what we want to learn. So a machine learning model is basically a function that if we query this function with an arbitrary input, this function is going to return a class. Okay, this is what we call a predictor. And at test time, given in UX, we are going to predict a y hat. So the hat denotes that this is a prediction made by our model, which consists in just applying this function to this input x. Okay, and hopefully, if our model is good, we want y hats to be as close as possible to y most of the time. And I'm going to be more precise about what this means, being close to the true y. All right. So the slide transitions are a bit awkward. Okay, now it seems that it's working. So, I didn't enter into details about the output space y. This was on purpose. Things can actually go by different names depending on what this output space is. So, for example, if the output space is continuous, for example, if it's the real line, then this is called the regression problem. So an example of such a problem is the input being a news article, and the output being how much time a user will spend reading this article. Okay, so this is a continuous quantity. Okay, it's time in seconds or minutes. And when the variable is continuous, this is called regression. We also have multivariate regression if we are trying to predict multiple dimensions at the same time. So, for example, if the input is an image, and if you want to predict what are the coordinates in the image where the user is going to click. So another example is classification. Okay, so this corresponds to discrete output variables instead of continuous. So the simplest example is the one that we talked in the beginning, binary classification. So in this case, we can, without loss of generality, we can assume that our classes are -1 and +1. And spam detection is an example of such a task. Okay, we can assume that spam corresponds to +1 and not spam corresponds to -1. And another example is multi-class classification, where our output space contains k labels, where k can be bigger than 2. For example, topic classification fits this setting. And we also have things that are more complex, like structured classification, where the output space can be exponentially large and structured. This happens, for example, in machine translation, where the input is a string in one language, and you want to generate a sentence in another language. In caption generation, where we have an image as an input, and we also want to generate text, or in image segmentation, where we want to find a segmentation of an image. And in all these cases, the output can, can be infinite. There's infinitely many sequences that we can generate, or if not infinite, it can be exponentially large in the size of the input, which is the case for image segmentation. So in this talk, we are going to stick with multi-class classification and binary, which is a particular case of it. We are not going to get into structured classification, but later at LXMLS, we are going to consider also structured classification. So keep posted to Xavi's lecture on Saturday, if I'm not mistaken. All right, so sometimes we can actually jump from these problems to another by doing reductions. So for example, we can reduce classification to regression by doing logistic regression, which is something that we are going to talk about today. We can also use a binary classifier to solve multi-class classification problems by doing a strategy like one versus all. Or we can do greedy search to reduce structured classification to multi-class. But other times it's actually better to tackle the problem in its native form. And this is the approach that we're going to take in this lecture today. All right. So one important aspect in linear classifiers, maybe the most important one, is designing good features. So this is sometimes called informally feature engineering. And so examples of that, so this is of course very problem specific, and it really depends on the kind of inputs that we are dealing with. So if our inputs are text, then popular features are bags of words. So this is basically just looking at which words occur in a document the number of words each word occurs, or a binary label if it occurs or it doesn't occur, can be our choice of feature. If we are dealing with text, other popular features also includes lemmas, part of speech tags, morphological tags, dependency trees, and things like that. I'm not going to get into details, so don't worry if you don't know what those things are. There's going to be some lectures in LXMLS that are going to present in more detail these kind of structures used in natural language. If we are dealing with images, then sift features, they used to be very popular some years ago, or wavelet representations. And in general, we can build arbitrary, categorical, Boolean, and continuous features. I'm going to show some examples. But so before doing that, just a little bit more notation. So the goal of having features is to represent information about our inputs, X, okay? And the typical approach is to define a feature mapping, so a function phi, that maps from X to a Euclidean space, a d-dimensional Euclidean space. And so each dimension of this space is a feature, okay? So we have d features in this case. And the number of features can be very high, okay? So phi of X can be a I-dimensional feature vector. So as we do this feature mapping, we are transporting our points to the Euclidean space, and we know how to do geometry and math in the Euclidean space. So this makes things more convenient for us. We can also use feature vectors to encapsulate all sorts of features, including Boolean ones, categorical ones, continuous ones, and so on. For example, if you have a categorical feature, so like a word in a vocabulary, then we can represent that feature as a one-hot vector. Okay, so for example, if the words chess occurs in a news article, about games, then we could assume that our feature space is the entire vocabulary, so it contains all possible words in a language, and we are assigning the value 1 to the word chess and 0 to all the other words. So this is what is called a one-hot vector, a vector that is 1 in one dimension and 0 in all the other dimensions. And so if you want to use words as features, we can just allocate a part of our vector space to be representing possible words in the vocabulary. And we're going to show some examples of how to do that in the sequel. Another example is for continuous features. So we actually saw an example right in the beginning of the lecture when we talked about the last layer in the neural network to be just like a linear classifier. In that case, the neural network learns features for us. We don't need the feature engineering step. But if we look at whatever these neurons are representing, they are typically representing real numbers, right? So, if you want to focus on the classifier that is going to fit the model to those features, it will have to deal with these continuous features. Other examples that occur in practice are, for example, when we start with combinatorial with discrete features and then do a lower dimensional projection with PCA, for example. We will end up with the continuous features, and then we need to deal with those features. And of course, continuous features are fine because the way we define the feature vector, we define it as mapping to a point in the Euclidean space. So this point can have continuous coordinates. All right. So in natural language processing, which is kind of an underlying theme of this summer school, it used to be the default choice of modeling to use an NLP pipeline, which consists of stacking together several linear classifiers. So today there was a kind of a change of paradigm. It's more common now to see systems that are trained end-to-end with a neural network. But this architecture still exists, and they are kind of a good motivation to explain linear models. So the way they work is each classifier's predictions are used to handcraft features for other classifiers. For example, some features that could be used here are word occurrences, binary features that denote if a word occurs or not in a document, or word counts, where rather than just denoting if the feature occurs or not, we can count how many times a word occurs in a document, like how many times the word chess occurs in a news document about some event, or part of speech tags, which could be, for example, how many adjectives or how many times a particular adjective occurs in a sentiment analysis problem. Other features could include spell checkers that are counting misspellings. These are particularly convenient in spam detection, and so on and so forth. And we can stack linear models on top of each other if you want to build systems to perform more complex downstream tasks. So let me give you an example. So the problem here is quality estimation of machine translation. This is actually a problem that I work on in my research. And the motivation for this is that machine translation is not solved. So if you use Google Translate, you might have noticed that it got a lot better in the last years, but sometimes it still hallucinates or gives a very bad translation. So this was an example. I think it might be outdated. But if we tried this some months ago, you'll get a wrong translation, in this case from English to French, because the system was assuming that the word work was a noun instead of a verb. Okay, so it was being translated as travail in French. So this is the wrong translation, and the goal of quality estimation is to assign a quality score to a given translation. Okay, without any reference. Okay, so if you have a system like that, this could be extremely useful. Because we could, if you are users of Google Translate or any other off-the-shelf machine translation system, we will not publish text that is flagged as being low quality. And the state of the art right now is using neural models, and it's much better than what we had a few years ago with linear models. But this screenshot or this example is from examples of handcrafted features that were developed for this task. And this was from models that were state of the art like 5 years ago or something like that. And this included, for example, counting the number of tokens in the source and target segments. If the number of words is very different in both sides, this makes this output suspicious. Of course, per se, this feature is not enough. So you need to combine this feature with a lot of other features. Another feature that is useful is the language model probability of the entire source segment and the entire target segment, and their ratio to see if one sequence is much more probable in the source language than it is in the hypothesized machine translation. And there's a lot of other features that could be relevant. And of course, if you look at the descriptions there, some of them you don't understand what they mean. This is because doing good feature engineering requires some expertise about the problem that you're trying to solve, which makes it harder for someone who doesn't have good domain knowledge to develop. But on the other hand, if you are a company developing a system like this, you might want to leverage the expertise. So if you have prior knowledge about your problem, it's good to use it, right? And feature engineering is an opportunity for using it. But yeah, so in general, feature engineering is a black art. It can be very time consuming. As I was saying, it's a good way of encoding prior knowledge. And this is particularly convenient if you don't have enough data to train your models. But there is one alternative, which is representation learning, which is what we do with the neural networks. And Bikshay Rai will talk about that tomorrow in his lecture. Actually, I think this afternoon. Right? So this evening, there's going to be a lecture on neural networks, which is going to be all about representation learning. Okay, so let me jump to regression. I'm going to take a look at the chats to see if there are any questions. Okay, I don't see any questions here. Just guesses about the label in that first example. Good. Okay, so let's start with regression. And let's start with a very, very simple problem. So in this example, we are assuming that the output space Y is continuous. So the simple example is we are given an article, and you want to estimate how long a user is going to spend reading that article. And if you have used Medium, you might notice that when you click on a story, there is an estimate there about how much reading time is estimated, like a 7 minutes read, something like that. And you might be wondering how they compute that. They probably use something super simple, nothing fancy. That's what I suspect. But in this simple example, we're going to think about how we could go about solving that problem. So in the simplest version, we could assume that X is just the number of words of the article, and Y, so the quantity that we want to estimate, is the reading time in minutes. Okay, and the goal is to define a model that predicts Y hats from X. All right, so, and let's suppose that we can get some data. So we are logging the time that users spend on these articles, and we get this cloud of points. Okay, so this is representing in the x-axis the number of words, in the y-axis how many minutes people are spending reading the articles. And this is just synthetic data that are generated. It's not real data. And let's suppose this is what the data looks like. And let's suppose that you want to start really simple, and that we are going to design a model that is going to select y hats as an affine transformation of x. Okay, so in other words, we are just going to predict the reading time as some coefficient w times x plus b. Okay, and the goal is to fit these model parameters w and b. So we have two parameters to fit them to the training data, which are these blue points in this plot. Okay, how can we do that? The simplest method to do that I'm guessing that many of you already heard of in high school, is the least squares method, which uses as a criterion to minimize the squared error. Okay, so in this case, what we want to do is to estimate w and b that minimize the sum of the squares of the difference between yn and yn hats. Okay, which is this affine expression depending on x. Okay, so, and if you want to fit w and b, we need to solve this optimization problem, minimizing this quantity with respect to w and b. So if you do that, we will end up with the w and b that represents a line, because this expression for y hats is representing a straight line in 2D, and this will be the best fit that we would get with this data. Is this a good fit? What do you think? Doesn't look great, right? It's not terrible, but it's kind of missing a little bit. When the number of words is very small, our estimate is over predicting the reading time, and the opposite happens. No, actually, the same thing ends up happening if the document is too long, and in the middle, it's kind of underestimating that time. So it's not the best model to solve this task, but it can be like a good first step. So we can actually do a little bit better than that. Often assuming just a linear dependency on y hat on x is a poor assumption. So our second take is going to be a little bit more general. We are going to design a feature vector, phi of x, instead of working with x directly, so that we can use more features from our documents. And of course, in real life, we could use a lot, any feature that we want. We could look at the words in the documents to see if these words are, in a very they're using very specialized terminology that will require a long reading time for people to understand the document or something like that. Here, we're not doing anything like that. This is just a very simple example. I'm just going to assume that the feature vector is like polynomial features up to some degree with respect to x, which is the number of words in the document. And we are going to add also a constant feature of 1, okay? Why do we want this constant feature? So what we're going to do with these features is we are going to make our prediction y hats to be the result of the dot product between a weight vector w and our feature vector phi of x. Okay, and if you recall the definition of dot product that you saw yesterday in Mario's class, then this is going to expand as a weight multiplied by this constant feature 1 plus a weight multiplied by x plus a weight multiplied by x squared, and so on and so forth. And this weight that multiplies this constant feature is going to act exactly like this bias term. Okay, so in other words, having a constant feature, saves us from the hassle of having to have a bias term explicitly in the model. Okay, and this is something that I'm going to come back several times throughout this talk. So in many cases, I don't want to, be writing this bias term over and over all the time. So I'm just going to assume that the feature vector has a constant feature, and this is going to imply that one of the weights is going to correspond to this bias term. Okay, so if you have a model like this, we can again use the same criteria of least squares and fit the weight vector W, which is our model parameters, by minimizing the sum of squared errors. So minimizing the sum of the squared differences between yn and y hat, where y hat consists of this dot product between W and phi of xn. Okay, and I'm going to spare you to the mathematical details, but if you solve this optimization problem, which we can do by just computing the gradients of this expression and equating it to 0, then you will obtain this closed form solution. Okay, so this is actually one of the rare instances of machine learning problems that you can solve in closed form, which is quite convenient. Okay, so so the solution has this form. So we need to form this matrix X. This is often called the design matrix. And the rows of this matrix contain the feature vectors for every training example. Okay, so each row corresponds to an example xn, and we just put here the transposed feature vector, like a row vector, corresponding to that point. So this is going to be a matrix number of examples times number of features. And we also need this vector y, which contains all the targets of the training set on the same order. Okay, so for each training point, we have the reading time corresponding to that data point. So the number of rows on y is the same as the number of rows on x. And then we just, to compute the closed form solution, to fit the model to the data, we just need to compute this expression, x transpose x, inverse of that, times x transpose times y. If you are familiar with linear algebra, with the notion of pseudo-inverse, you might recognize this transformation of x before multiplying by y as the pseudo-inverse of matrix X. Okay, so this is still called linear regression, and the reason why this is called linear, even though we have polynomial features and we don't assume that our model has a linear dependency of y hat on x, but it's still linear with respect to the weight vector. Okay, so if you look at the expression for y hat, it's a inner product, it's a dot product between the weight vector W and the feature vector phi of x. So linear models means linearity with respect to the model parameters. Okay, and this choice of model still satisfies that. Okay, so I see that there's a few questions. So I'm going to look at some of these questions. What are other alternatives to feature engineering other than representation learning? This is a great question. I'm going to talk a little bit in the end of this lecture, if there is time, about kernel methods. So one alternative to feature engineering is trying to design similarity functions that compare inputs. And if you have some properties in that similarity function, we can use kernel methods to develop methods. So besides representation learning and things that we can do with neural networks. There was another question. You mentioned that the bag of words model can be represented as word occurrences versus word frequencies. What is the default setting? So both are used in practice, and they correspond to different assumptions. Like in one case, we assume that a document is represented by a word occurring or not. In the other case, we assume that there is like a multinomial distribution that represents a document that counts how often you get an outcome, which is a particular word. And typically, you want to use the frequencies if you are dealing with longer documents, where the number of occurrences of a word is going to help you more than just knowing if a word occurred or not. There was another question, do feature vectors have to be of the same dimension and size? So yes, we if we are working on a fixed problem, we need to stick with the fixed dimension for the feature vector for this to make sense. Okay, because for these linear models, for example, in this example that I just showed, you are talking about the inner product between the weight vector and the feature vector, and we assume that the number of parameters in our model is fixed, and it corresponds to the number of features. Anecdotally, do spelling errors correlate positively or negatively with spam? This is a great question. I don't know. I would say that my first intuition is that they correlate positively, but depends on what is the domain of the text that we are looking at. If you are looking at text that is curated, probably it's not going to have a lot of spelling errors. If you are looking at user-generated text, then yes, probably it's going to have a lot of spelling errors. And also, the quality of spell checkers is also, sometimes not great. Okay, so it's not going to detect all spelling errors that exist in text. And in practice, it's an open problem to develop better spell checkers. All right. Let me look at chats to see if there is anything else. What is the impact of including omitting the intercept term in the regression equation? So I might have answered that question already when I mentioned the possibility of using a constant feature. So usually we need, unless you have a good reason to believe that the intercept term is 0, which is rarely the case, you need to include the intercept term. And now there are two ways of doing it. Either you have the bias explicitly in your model, or you assume that your feature vector has a constant feature, which is equivalent, but you need to include it. Otherwise, we could be making a very poor estimate for most of the problems for which we are applying regression. All right, so I'm going to move on. So this was what we got with a single feature, with the linear relation between y hats and x. If we use if you use a second degree polynomial, so if you use this one additional feature, then you'll get a much better fit. Okay. So this looks much better now. I think it's going to be a more realistic model for this problem. And if you overshoot, if you have too high of a degree, things will overfit. And I'm going to talk a little bit about overfitting in a while. So everything that we have seen with this regression example uses a particular kind of loss function called the squared loss. So linear regression with the least squares method, it corresponds to minimizing the sum of the square differences between y and y hats. And we can scale it by 1/2. You might, if you never saw this before, you might be wondering why we have this 1/2 here. Don't worry about that. This is just a scale factor. If we minimize this loss, it doesn't matter if we multiply it by a constant. In practice, this 1/2 is convenient if you are computing gradients of this expression, because some terms will cancel. But so overall, what these methods are doing is to posit a function representation for y hats, which in this case is linear with respect to the weights, and minimizing the sum of terms like this, y minus y hat squared. And we're going to come back to this topic later when we compare different loss functions. It's also possible to interpret least squares probabilistically. And so if we assume that the data is generated stochastically like this, so if you assume that the true model corresponds to some parameter vector W star, and we want to identify this true model, so this is a very frequentist assumption, then we can assume that the data is generated by taking the dot product between W star and the feature vector phi of x and adding noise. Okay, and if you assume that the noise is Gaussian with 0 mean and variance sigma squared, where the variance is fixed, then y becomes a sum of a deterministic part, which is the part that only depends on the dot product between w and phi of x, and the stochastic part, which depends on the noise. And because we are adding a Gaussian random variable to a deterministic number, the distribution over y, if you remember yesterday's class from Mario, it's going to be a Gaussian with mean w star dot product with phi of x and variance sigma squared. Okay, so y just inherits the variance from the noise. And so it turns out that the least squares method that I just presented corresponds to maximum likelihood estimates under this model. And I have a one slide proof that shows this. Okay, so if we recall that Gaussian distributions have this parametric form, then maximum likelihood estimation corresponds to finding the model parameters W that maximize the probability of the data, the training data, given those parameters. Okay, so you want to pick the W that maximizes the likelihoods of the training data. And if you assume that the training data is generated IID, then the probability of the training data is the product of the probabilities of each data point. Okay, and because we are assuming that the probability of y given x is Gaussian, then we can use the form of the Gaussian distribution and solve these with respect to w. Okay, so the first thing that we are going to do is to note that maximizing the product of probabilities is the same thing as maximizing the log of that, because the log is a monotonic function. So we can just maximize the log of these products, and then the log of the product is the sum of the logs. Okay, this is one of the key properties of logarithms. And therefore, we can equivalently write this as maximizing the sum of log of p for each data point. And now, by taking the log of this Gaussian distribution, this is again a product of two terms. The log of these equals the log of the first term plus the log of the x of the second term, and then log and x cancels. So we get this expression that I have in the third row. And because we are assuming that the variance is fixed, we are not trying to estimate the variance, then this term is a constant, so it doesn't affect the argmax, so we can get rid of it. And sigma, the variance also appears in this term, but this is now going to be just a scale factor. So finding the W that maximizes this entire thing is the same thing as finding the W that minimizes, because we flip the sign, the W that minimizes the sum of the squares. Okay, so we have just proved that linear regression with the squared loss is equivalent to maximum likelihood estimates under Gaussian noise. Okay, so there is a question in the chat about d equals 2. I'm guessing that, so you mentioned that d equals 2 works better, but I'm guessing that means that model predicts for some I number of words a decreasing amount of time needed to read it, which contradicts our intuition. Here the issue, I believe, is something around the idea that we just check validation on data instead of setting some invariance. Yeah, so this is a very toy example, right? So in a, of course, if your document has, an infinite number of words or a very large number of words, a quadratic function like the one that I was showing is, of course, not suitable, because it will predict like a negative, reading time at some point. But if you only want to do regression in a limited region of space, then this d equals 2 is a reasonable assumption. But it's and this is typically something that we encounter in practice. Like, we don't want to approximate regions of the space where data doesn't occur. We care about approximating regions of space that are that have high distribution according to the to the mechanism that generates our data. So I'm not going to talk about a very relevant problem, which is generalization to out of domain points. But yes, this was just a simple example. Don't take it too seriously. There is another question. Can we explain the consideration of W transposed phi of xn is mean? I'm not sure I understand the question. Maybe it's related to these slides. I think it's probably the previous one. I see. So so y is defined as the sum of the deterministic term, because W star transpose phi of x this is not a random variable. This is a deterministic quantity, even though we are dealing with an unknown quantity or unknown vector, which is the true model parameters. But when the model when the data is being generated according to the model, there is this deterministic part, and then there is this stochastic part, which corresponds to the noise. And if you are adding a constant to a Gaussian random variable with mean 0, the sum is going to be Gaussian with mean equal to the constant part and variance equal to the variance of the stochastic part. Okay, so this is just a simple formula to compute the parameters of a Gaussian distribution that is a simple transformation of an existing Gaussian distribution. Okay, I think there was an example in Mario's slides yesterday with a more general expression for the case where y is an affine transformation of a Gaussian. So this is a particular case of an affine transformation where we are just adding a constant to the original Gaussian distribution. Okay. Right. So moving on. So we talked about the squared loss. In the real world, there are other loss functions that can be useful. For example, the absolute error loss. Instead of penalizing the square of the differences, we penalize the absolute value of the differences. This corresponds to this blue line here. And so the squared loss corresponds to this red parabola. And there is something in between called the Huber loss, which is defined like this. So between -1 and 1, it corresponds to the squared loss, and then it reverts to the absolute loss. So it becomes linear when the error is greater than -1 or 1. So when the absolute value of the error is greater than 1. And the Huber loss is often used in cases where we don't want to penalize outliers too much. So one of the problems with the squared loss is that if you're working with a problem where there are some outliers, then they will get a very heavy penalization, and as a result, you could get a very bad estimate according to our model, because the outliers can be pushing your your line too much. And the Huber loss is less sensitive to outliers, so it's a more robust loss if you have outliers. So yeah, there's plenty of other choices. These are just a few examples. So I talked before about overfitting and underfitting, but let me be a little bit more precise. So actually we saw the example where we try to fit with d equals 1, that simple problem. It was a classic example of underfitting. Our model was, it has too few parameters. It had only 2 parameters, a weight and a bias. And this was too little to fit to the data. So a straight line was not enough. But we also have the reverse problem. If we define a model that is too complex, if it has too many parameters, for example, if you are using too high of a degree for the polynomial, then we run the risk of overfitting. So we could get something that looks like this plot on the right. Okay, so it could fit perfectly the training data. We could have 0 training error, but the model might not generalize well to unseen data. And so in general, we need to balance between underfitting and overfitting. And the way to do that is to have a regularization term. And we're going to talk about that in the second part. Actually, there is kind of a teaser example now. I'm going to go quickly through this example in the interest of time. But so if you remember the connection that I made before between least squares and using Gaussian noise and maximum likelihood estimates, this is like an elaboration of that example that corresponds to using regularization. So let's suppose that we have now a prior distribution over our weight vector. So let's suppose that our prior tells us that our weight vector, we believe that our weight vector is not too big. So it is distributed as a Gaussian variable with 0 mean with some variance sigma squared W. Okay, so it's a very simple prior. And one criteria to estimate the parameters is using maximum a posteriori or map inference. And this corresponds to picking the W that maximizes the probability of W given the data instead of the probability of data given W, okay? And if you use Bayes' rule, because the data is observed, this is equivalent to maximizing the joint probability of W and the data, okay? And using our assumption, we can write it as the probability of the prior P of W times the probability of the data given W, okay? And the probability of the data given W is what we had before. So the only thing that we are adding in this slide compared to MLE, maximum likelihood estimation, is the addition of this prior that multiplies our objective function. And because we are assuming that our prior is Gaussian, when you take the log of this, we just get this extra log of PW term, adding to the term that we already had before. And this will correspond to, if you use the formula for Gaussian distributions again, this will correspond to the squared L2 norm of W divided by 2 times the variance. Okay. And so at the end of the day, we end up with an objective that looks like this, where this lambda corresponds to a ratio between the variance of the prior and the variance of the noise in the data generating process, and minimizing, so finding the W that minimizes this is like a regularized version of least squares, which is called ridge regression. Okay, so, and this is an example where we have, where we are using the L2 norm as a regularization function. Okay, this is called L2 regularization. And we're going to talk a little bit more about that in the second part of the talk. So the punchline here is that L2 regularization is equivalent to maxima a posteriori with a Gaussian prior, if you want to have a Bayesian perspective on these problems. All right, so this finishes the part on regression. What time is it? Okay, so I think we need to have a break in half an hour. So I'm going to try to cover Perceptron and naive Bayes in this half an hour and do the break out afterwards. So we are now going to switch to classification, and we are going to start with binary classification. So here we assume that the output space has 2 labels, okay? And without loss of generality, we can assume that the labels are -1 and +1. You can assume, for example, if you are working on a fake news detection problem, the input is a news article, and the goal is to detect if it's true or fake. We can assign the label +1 to true and the label -1 to fake. So the question is again, how can we define a model that predicts y hat from x? The simplest way of doing that is again to use a linear classifier. So the idea is very similar to what we did in this simple regression example, but with a small twist. Okay, so we still form this affine function W, the dot product between a weight vector and the feature vector phi of x plus a bias term, but now we are using a sign function in order to obtain an estimate for y hats that is a label +1 or -1. And the sign function is just a simple mathematical function whose value is +1 if the argument is positive and -1 if the argument is negative. And it's undefined when the argument is 0. Well, in this case, we are just conventioning that it's +1 if the argument is 0. But that situation is not going to arise frequently in practice. So we don't need to worry so much about 0. All right, so basically you can interpret the the thing that is inside the sign as a score for the positive class. If this score is positive, then the model is going to predict +1. If this score is negative, then this model is going to predict -1. Okay, so the only difference from regression is that the sign function is doing this conversion from continuous to binary. And now the decision boundary is going to be an hyperplane, which is defined by the model parameters W and B. Okay, and for this reason, this is also called a hyperplane classifier. So this is what it looks like geometrically for a simple problem that has only a single feature and a bias term. So the parameters W and B parameterized a straight line, which is represented here. So this is the equation W dot product between W and phi of X plus B equals 0. And then this hyperplane is splitting the feature space into two regions, two half spaces. One half space that's where the predictions are always going to be +1, and one half space where the predictions are going to be -1. And hopefully you want this hyperplane to fit the training data. So if the training data consists of these minuses and these pluses, we want the hyperplane to to separate these two data points, these two sets of data points. Okay, so the question now is, how can we learn such an hyperplane from training data? Okay, so there is a question, very good question. Will there be any difference in defining classification labels as -1 and 1 versus 0 and 1? How are the change in these labels are going to affect the model? So in practice, there's not going to be any difference. You need to convert one to the other. But the question is very pertinent because many textbooks, instead of conventioning that the labels are -1 and 1, sometimes it's more convenient for some models, like logistic regression is an example of that. Sometimes it's more convenient to assume that the labels are 0 and 1. And everything that I'm going to describe for -1, 1 is easily generalizable for 0, 1, because we can easily, if you have a label y hat that can be either -1 and 1, if you divide that label by 2 and sum 1/2, you map it to 0 and 1. Okay, so it's very easy to map from one to the other. All right. Oops. Okay, give me a second. I lost my screen. All right. Okay, so how can we learn this hyperplane from training data? There is a very important concept called linear separability, which is defined like this. A data set is said to be linearly separable if there exists a choice of parameters W and B such that the classification is perfect. So the example in the right is a data set that is separable because we can find an hyperplane that separates the plus examples from the minus examples. The data set on the right is not separable because it's not possible for any hyperplane to separate the minus from the plus because they are kind of interleaved. And we next are going to talk about a very simple algorithm called the perceptron algorithm that is guaranteed to find such an hyperplane if the data is linearly separable. And this is one of the earliest instances of a linear classifier. So before going into that, let me just state something that we already saw in regression, but it also holds in classification. We can get rid of the bias term if we assume that one of the features is constant. Okay, it's pretty much the same argument. If the first feature of phi of X is 1, then the corresponding weight term can be interpreted as a bias term. And so if you assume that you don't have a bias term, then the decision boundary is going to be an hyperplane that passes through the origin. So you're just augmenting the feature space with one additional axis to account for that bias term. And we can always do this without loss of generality. Okay, so let's move into the perceptron algorithm. First, like a quick historical perspective. This algorithm has been invented in the late 50s by Frank Rosenblatt. It was actually implemented in hardware with this device called the Mark I Perceptron, designed for image recognition. And it was, as you can see, there's a lot of wires here. So the weights of the model were actually weights encoded by potentiometers, and the weight updates were performed by electric motors. So this is like a mechanical device that emulates the sort of algorithms that we are talking about today. And when this was proposed, there was a big buzz in the news. So this is a news article from New York Times in '58, announcing the news that there was a new Navy device that learns by doing. And you can look at some of the paragraphs, and you can note very bold claims there, like Dr. Rosenblatt, a research psychologist at the Kernel Aeronautical Laboratory, said perceptrons might be fired to the planets as mechanical space explorers. And later, we have these later perceptrons will be able to recognize people and call out their names and instantly translate speech in one language to speech or writing in another language. Mr. Rosenblatt said in principle it will be possible to build brains that could reproduce themselves on an assembly line and which will be conscious of their existence. So very, very bold claims. It's not from today's times that there is a big PR and some exaggeration about the accomplishments of AI. But it was, the perceptron was really a remarkable invention at the time. What I really like about the perceptron algorithm is its simplicity. So it's a very, very simple algorithm that comes with theoretical guarantees. So it's an instance of an online algorithm. So it processes one data point in our training set at each time. And the way it works is the following. It first samples a point randomly. Let's say it samples point xi, and it applies the current model, the current version of the weights and biases, to make a prediction for this point. And then two things can happen. If the prediction is correct, the model does not do anything and just sample another point. If the prediction is wrong, then it needs to perform a correction for the model. And this correction is with a very simple update rule that is just adding or subtracting the feature vector from the weights. And so, I'm going to give you the pseudo code, and I'm going to omit the bias term for simplicity. So we're just going to assume that there is this constant feature that I was mentioning before. So this is the pseudocode for the perceptron. It's really just a few lines of code. So the input is our labeled data set. We initialize our weight vector to 0. We keep track of how many mistakes the perceptron algorithm is doing. This is stored in this variable k. And then, at each point we have this infinite loop. At each point we get a new training example, xi, yi. We make a prediction using our current model, which I'm denoting here by w superscript k. So we obtain y hi hat, and then if y hi hat is correct, we don't do anything. We just jump to the next iteration in the loop, sampling a new training example. But if there is a mistake, then we do an update, and this update is just applying this simple rule. Okay, so the new weight vector at iteration k plus 1, it's going to be equal to the previous one at iteration k plus yi times phi of xi. Okay, so if yi is plus 1, so if the correct label is positive, then this is adding the feature vector corresponding to xi. If yi is minus 1, so if the correct label is negative, this is instead subtracting the feature vector from the weight. So the intuition here is that by doing this addition or subtraction, we are correcting the model weights so that next time we see this point, it will be more likely that it will predict the correct class. And we also increment k because this is accounting for the mistake that the perceptron did. And you just do that until either we find an hyperplane that separates the data, or until we reach the maximum number of rounds. And the output, it's going to be the model weights. Okay, so it's a very, very simple algorithm. But it turns out that this simple algorithm comes with some theoretical guarantees, which is quite remarkable. So before introducing those guarantees, I need to add a couple of definitions. The first one is that the training data is called linearly separable with a margin gamma. So this is kind of a formalization of the notion of linear separability that I had in the previous slide. So we say that the margin of separation is gamma, where gamma is a positive number. If there is some weight vector u normalized, so a vector with norm 1, such that for any data point, this quantity on the left is greater than or equal to the margin. So this means that if the label is positive, this U transposed phi of xi is the score that the model assigns to that class. So this means that the score, if the label is positive, the score is bigger than gamma. If the label is negative, the score is less than minus gamma. Okay, so this is kind of, you can see this as some kind of notion of confidence that the model is given. And the data is separable if there is an oracle weight vector U that allows to achieve this margin. And the second definition is the radius of the data. Okay, so we need this because we need to have a way of quantifying what is the scale our data is presented, and we define it as the maximum norm of phi of xi, and the radius is denoted by this quantity r. So given these two definitions, we have the following mistake bound for perceptron, which is very famous. It's a theorem due to Novikov that states that if the data is linearly separable with a margin of gamma, then the perceptron algorithm is actually guaranteed to find a separating hyperplane after at most doing this number of mistakes. Okay, and intuitively you can see that the lower the margin, this means the harder it is to find an hyperplane that separates the data. Okay, because there is less room for finding such an hyperplane. So the lower the margin, the higher becomes the total number of mistakes. On the other hand, the lower the radius, or the higher the radius, the higher number of mistakes as well, because this is controlling for the scale of the data. So this is a very powerful result, and it turns out that it's actually very simple to prove. The proof fits one slide. And this is the slide. So I don't resist. I don't have any other proof in this talk, but I cannot resist to present this one. It's very elegant. So here I'm starting by recalling that the perceptron updates as this form. So we are just adding yi times phi of xi to the previous version of the weight vector. And the way we're going to prove this is by first computing a lower bound. On the norm of W after doing these updates, and then doing an upper bound. So the lower bound, we can do the following. So recall that U is this oracle weight vector that is guaranteed to exist because we are assuming that the data is separable with a margin of gamma. So we don't know which U, what is this U. This is what we are trying to find out. But we know that there is some U, okay, and we can plug it in the proof. So we start by writing the dot product between U and W after performing the updates. And by using this expression for W k plus 1, you can get this expression for after the updates. And because we know that the data is separable with a margin of gamma, we know that this second term is greater than or equal to gamma. And if you apply this inequality k times, then we'll get that this inner product between U and W k plus 1 is greater than or equal to k times lambda, k times gamma. Okay. So now, because we know by our definition of margin that U is normalized, this was this assumption here that the norm of U is 1, then the norm of WK plus 1 equals the norm of U, which is 1 times the norm of WK plus 1. And now we can use Cauchy-Schwarz inequality, which I think Mario presented yesterday in his introductory class, to bound the product of the norms to lower bound it as the dot product between U and WK plus 1, which is what we had in this previous expression. And as a result, we know that the norm of WK plus 1 is going to be lower bounded by k times lambda. Okay. And the second thing that we do is to have an upper bound of the same norm. And to do that, we just compute the square of the norm, plugging the expression for the updates. Expanding this square, we get this expression in the first line. And now we know that the second quantity needs to be less than or equal to 0 because the model did a mistake. So this means that either the class is positive and the score was negative, or the class was negative and the score was positive, right? Because we only do a perceptron update when there are mistakes. So this part, this term is less than or equal to 0. And this term, it can be upper bounded by the radius of the data. This was the second concept that I introduced in the previous slide. And therefore, the squared norm is upper bounded by the squared norm of W before the updates, plus the squared radius of the data. And if you apply this inequality k times, then we get this upper bound. And now we have a lower bound on the norm and we have an upper bound on the norm. So we can just put the two things together. Equating both sides, we get that k gamma squared is upper bounded by k r squared. And as a result, we get that the number of mistakes k is upper bounded by r squared divided by gamma squared. Okay, this is exactly how we prove Novikov's theorem. So if you didn't follow all the details, don't worry, this is not going to be important for the rest of the talk. We can always take a look later at this slide if you want to understand this better. But the point here was just to show that this proof is actually quite simple. Okay, so there is a question, could you give an intuition of the notion of separating hyperplane in Novikov's? Yeah, so this is exactly the definition that I had. So this is the theoretical definition. If we go back to the picture where I had linear separability, right here, the margin corresponds to the distance between. So for the best choice of hyperplane, the distance between the closest points on either of the classes and the hyperplane. We are going to come back to this topic when we talk about SVMs in the second part of the talk. But so the higher the margin, the higher the distance between these two sets of points and the hyperplane. So there's a few more questions. Did you mention if the perceptron can recognize that the data is not linearly separable? That is a good question. So I don't think we have the guarantee that it can identify that the data is not separable in a finite number of steps, because we don't know the margin beforehand. But if you run the perceptron for a long number of steps and it's not converging, this is a strong indicator that maybe the data is not linearly separable. So yeah, I think what you suggest is accurate. And in practice, we also observe that perceptron tends to oscillate in those cases. All right. Okay. So so the perceptron, as you saw, is very simple. It has these theoretical guarantees, but it's not infinitely powerful. Okay. So we cannot do the things that were written in the New York Times just with perceptrons. And let's first look at what the perceptron can do. So it can solve any linear separable problem. So for example, if you are computing a logic function with several arguments, it can compute, it can learn the OR function or the AND function. So this is represented schematically here. If x1 and x2 are Boolean functions, zeros and ones, and the classes are represented by OR of x1 or ANDs of x1, then you can easily find a separating hyperplane, and the perceptron will eventually find this hyperplane. But if you have a logic function like the XOR function, which is this famous example that breaks the perceptron, then the perceptron cannot solve it. And the reason why it can't solve it is that if you plot the XOR function, you'll see that the XOR is going to be 0 if the classes are the same, which corresponds to these 2 points, and it's going to be 1 if they are different, which corresponds to this other 2. And since these points are interleaved, there is no way an hyperplane can separate them. Okay, so it is not possible for not just perceptron, but it's for any linear classifier to separate these points in this original feature space. Of course, you can do feature engineering and transform the point representations to something more convenient that is linearly separable. So for example, if you define one of the points to be the end of negated x1 and x2, and the other one to be the end of x1 and negated x2, then these two circles collapse, and now we can separate everything with an hyperplane. But this required this step of modifying the features. Okay, and later tomorrow we are going to see that we can have a multi-layer perceptron that learns these feature representations for us. But so this negative result about XOR and perceptron is often attributed to a book by Minsky and Papert, but actually it was known well before. And this is the book. The book actually shows other limitations of multi-layer perceptrons. It is associated with the AI winter periods that happened afterwards. And I think Biksha is going to talk a little bit more about this tomorrow. Okay. So let's now assume a multi-class classification problem where we have more than two classes. If we are working in a problem like that, we could always try to combine different binary classifiers, each specializing in each of the labels. For example, trying to distinguish each class from all the other classes. This is called the one versus all strategy. Or we could train pairwise classifiers that compare each pair of labels and then use something like voting to come up with the final decision. But we are not going to do that here. So instead, we are going to consider classifiers that tackle the multiple classes directly. And if you want to talk about multi-class linear classifiers, then we need something different from the sign function, because we are not going to predict +1 and -1 anymore. So the way to do that is to consider a weight matrix instead of a weight vector, a weight matrix whose dimensions are number of classes times number of features. Okay, so this weight matrix is going to contain one weight for each pair of feature and label. I'm using the word label and class interchangeably. And we also need a bias vector that has a coefficient for every class. And so this is, you can think of this as having as many weight vectors as the number of classes. So each row in this matrix can be regarded as a specialized weight vector for that class, and one scalar for each class. And then if you do that, then we can compute the score of a particular label by doing a linear combination of these features and these weights. Okay, so for the label Y, we can compute the score of this label as the dot product between the vector WY and the feature vector phi of X plus the bias term BY. Okay, and if you compute scores for every possible label, so if you have, let's say, 6 labels, we can compute 6 scores, and you can just pick the label that maximizes the score. So the label that has the maximum score. So we are doing this via this argmax function. Okay, so we are going to predict Y hats that maximizes this score. So geometrically, this matrix W and bias vector B are going to split the feature space into regions that are delimited by hyperplanes. So this will be what would happen, if we have 3 classes, for example. And in neural networks, it's also very common to deal with output layers that have to deal with multiple classes. The commonly used notation in neural networks is this one. So we compute a score vector whose dimensionality is the number of classes by multiplying the matrix W by the feature vector phi of X. So this matrix vector multiplication is going to result in a vector whose dimensionality is the number of classes, plus a bias vector, and the dimensionality of this bias vector is also the number of classes. So the result inside the argmax is going to be a vector whose dimension is the number of classes, and then we return Y hat as the argmax of this vector. And by convention, this is often denoted as a one-hot vector, where Y hat indicates the label that has the maximum score with a 1, and all the other labels will be assigned zeros. So we are going to return this in the second part of the talk. Okay, so this sets up the notation. So let's first, as a sanity check, ensure that this multi-class formulation recovers the binary case. So if you only have two classes, if y is +1 and -1, and if you use the expression with the argmax that I just presented, so our predictions are going to be y hats among these two possible choices, +1 and -1, that maximize this score. Because there is only two possibilities, we can write it as +1 if the score corresponding to class +1 is bigger than the score corresponding to class -1, or -1 otherwise, right? And now if you rearrange the terms in this inequality by noting that they are all using the feature vector phi of x, we can equivalently write it as the sign function involving the difference between the weight vector corresponding to the class +1 and the weight vector corresponding to class -1, and the same thing with the two bias terms, the bias corresponding to the class +1 and the bias corresponding to the class -1. So if you reparameterize the problem by defining W to be the difference of these two weights and the bias to be the difference of these two biases, we just arrive at the formulation that we had before for the binary case. Okay, so with the benefit that you only need to concern with, we only have half of the parameters. Okay, so this is a pictorial example of linear classifiers for the binary and multi-class. So this is again our prediction rule for the multi-class case. Again, we call these linear classifiers because this is still linear in WY. This is what makes it a linear classifier, linearity with respect to the parameters. The decision boundary is defined by the intersection of half spaces. And in the binary case, as we saw earlier, this corresponds to a hyperplane classifier. And so once again, it's common to omit the bias vector B. Okay, so we can do exactly the same thing. We don't actually need this bias vector. We can just define without loss of generality. We can assume that we have a constant feature for every class. We have a constant feature phi 0 of x equals 1. And this means that the first column of our matrix W is replacing this bias vector. So we are going to have one entry on this matrix for every label indicating the bias associated to that label. And we are going to assume that from now on for simplicity. And so the first thing that we will see is that the perceptron algorithm also works for the multi-class case. In fact, it has a similar mistake bound. If the data is separable, then the perceptron is going to be guaranteed to find separating hyperplanes. And so in fact, what you need to do is just to slightly change our update rule. Instead of one update, you need to do two updates. So we need to increase the weight of the label associated with the gold class. And we need to decrease the weight associated with the incorrect class, the class that our model predicted, but it's incorrect. And again, if you don't do a mistake, we don't update anything. And we still have the same mistake bound if you do that. All right, so let me jump to naive Bayes. For a moment, let's forget about linear classifiers and let's go back to our probabilistic mindset. So let's assume that our goal is to model the conditional probability of the output labels y given our inputs x. So we want to model the probability of y given x. And if we have such a distribution, then we can classify with a Bayes classifier that just predicts the class that maximizes the probability of y given x. We just predict the most probable label according to our model. And so one way to model P of y given x is by using Bayes rule. Okay, so we can write P of y given x as a prior on the label, P of y, times the probability of x given y. This is the conditional probability of the data given the label, divided by P of x. When you are giving a new data point x and you want to predict y, we only need to maximize P of y given x. So this normalizing term doesn't matter because it's constant. Okay, so no matter what y is going to be, this term is always going to be the same. So this means that maximizing this quantity is the same thing as maximizing only the numerator. Okay, so we can write the problem of maximizing P of y given x as that of maximizing the product of the prior P of y and the conditional probability P of X given Y. Okay. And so far, I didn't make any assumption. This is just applying Bayes' rule. Okay, so one way of regarding this objective is by constructing a story about how the data is generated. And the story goes like this. Let's assume that nature follows this generative story. Nature is first going to pick the class, for example, picking if it's spam or if it's not spam. And then it's going to pick the input X given the label. Okay, so if decided to pick spam, it's going to generate an email that is going to be spam. Otherwise, it's going to generate a legit email. And so models that consider this joint probability distribution, the joint probability of X and Y, they are called generative models because they come with this sort of generative story. And so, tomorrow in Noah Smith's class is going to elaborate a little bit on this distinction between generative models and discriminative models. Okay, so now that we define this, so there is a question: does the unbalanced data set will affect a naive Bayes model? So I had not spoken about naive Bayes yet. This is what I'm going to talk about now. But regarding the Bayes rule that I showed you before, if the data set is unbalanced, then we will have a prior on the label that accommodates for that. So if one of the classes is much more frequent than another, then our prior or P of Y can represent that. So the Bayes rule should be robust to unbalanced data sets. Yeah, so we are going to have a short break. Let me just finish the part of naive Bayes, and then we'll do a coffee break, and we will come back a little bit later. But let me wrap up this part before, because there's a second part where more things need to be covered. All right, so let's assume that our inputs, for example, let's assume it's a document. Let's assume that it's partitioned as L features, V1 to VL, where we can assume, for example, these V's to correspond to words that occur in the document. And we can assume that our vocabulary is fixed. Okay, so all words are drawn from this vocabulary. Then if our input is partitioned this way, the naive Bayes assumption is stating this. So it's stating that the probability of the sequence V1 to VL, which corresponds to our input X that we are observing, given Y, can be written as the product of the individual probabilities of each VK condition on Y. Okay, so in other words, this is stating that all the V's are conditionally independent given the label. This is what naive Bayes assumption means. Okay, and so if you make this assumption, then we can write the joint probability of X and Y as a product of the probability of Y times the probability of V1 to VL given Y. And since we made this naive Bayes assumption, we can write it as the product of PY with the product of the individual conditional probabilities. So this says that all words are conditionally independent given the topic. And note that according to this model, the word order is not going to change the joint probability. So if you permute the order of the words, if you permute the VIs, then this is not going to change because they are only going to contribute to the final probability through this product. And so this is called the bag of words assumption. So in this description, there is a small caveat. We assumed that the document has a fixed length. We assume that the document has length L, which is not very realistic. In practice, documents, they have a varying number of words. So one way of dealing with the variable length is by having another distribution over the document length. I'm denoting it as P over, the modulus of X. This should be interpreted as the length of the document. And we can use something like a Poisson distribution, for example, to model the length. If you do that, nothing is going to change. You get an extra term that depends only on X. It does not depend on Y. And therefore, it's not going to influence the maximization of P of Y given X. Okay, so the short story is that you don't need to be concerned about the length of the document in this multinomial naive Bayes model. Okay, so what is this naive Bayes assumption buying us? What do we gain with it? Well, the thing that we gain is a huge reduction in the number of parameters. So if we haven't done any factorization assumption, how many parameters will be required for expressing this probability of V1 to VL given Y? Does anyone want to write in chat? V to the L. Exactly. So you get exponentially many parameters. So it goes exponentially with the length of the sequence that we are hypothesizing. Because we need to store a probability for every combination of words in the document. And this doesn't scale, right? It's just too many parameters. And if you have too many parameters, first you might have sparse observations. So you might not have enough data to estimate these parameters accurately. And it's also going to give us some computational problems because you need to store all these parameters. And with naive Bayes, how many parameters do we need? Yeah, so we need a linear number of parameters. Sorry, I just lost my screen again. Okay, so with naive Bayes, we only have a linear number of parameters in the vocabulary size because you only need to store the probability of vk given y. Okay, and this is quite convenient. So with less parameters, you have less computation, less risk of overfitting, though of course you might still underfit if our naive Bayes assumption is too strong. And how can we learn the parameters in a naive Bayes model? So again, the goal is to learn from data. We start with our data sets. Examples are assumed IID. The parameters that we need to estimate are the prior probability for each class and the conditional probability of a word given the class. And the objective function that we want to optimize is maximum likelihood estimation. So it's maximum likelihood. So you want to choose the parameters that maximize the likelihood of the observed data. If you do that, I'm not going to show you the proof, but if you do that, the solution is actually going to be very, very simple. It has a closed form. It all boils down to counting and normalizing. And we are going to see this today in this afternoon's lab. So the solution takes this form. Okay, so the solution for the priors is basically counting how often we observe examples in each of the classes and divided by the total number of points. So it's the relative frequencies. And for the probability of the words given a class, it's pretty much the same thing. So it's how often do you see that class? This is the denominator. And how often do you see that class co-occurring with that word? And this is the numerator. So let's look at one example before we do the break. Very simple example. This is for a sentiment analysis, simple toy problem. Let's assume that we have a corpus of movie reviews and we have only 7 examples for training. And these are our examples. And we are going to assume that our features are just adjectives. So we are ignoring all words that are not adjectives. And now we need to estimate our probabilities according to the naive Bayes model. So we first need to estimate the priors for the classes, and we see that we have 3 positive examples and 4 negative examples. So the probability of the positive class is going to be 3 divided by 7, which is the total number of points of examples, and the probability of the negative class is 4 divided by 7. Okay. Now the second thing that we need to estimate is the likelihoods. So it's the probability of each word given the class. Okay, so let's start with estimating the probability of amazing given positive. If you look at our data, you see that amazing appears twice in examples that have the class positive. And there's 3 examples with a class positive. Therefore, the estimate is going to be, sorry, so we have 10 total adjectives appearing in examples with a class positive. We have these ones, great, excellent, renowned, and so on. So there are 10 in total. And among these 10 occurrences, amazing occurs twice. Okay, so our estimate of the probability of amazing given positive, it's the number of times amazing occurs divided by the total number of times that any other adjective occurs in examples with a positive class. So it's 2 divided by 10. And the same thing can be done for the other adjectives occurring in positive examples, and the same thing for negative examples. So for example, amazing never occurs for negative examples. So the probability of amazing given negative is 0 divided by 8, which is 0. So this is what we do at training time. After doing that at training time, we can actually do predictions. Okay, so given a new segment to classify, let's suppose that we are given these new documents. This was a fantastic story, good, lovely, and we want to predict the class. We need to put together all these probabilities that we estimated at training time. So the probability of these, given by this naive Bayes model, it's going to be the probability of the class, the prior P of Y, times the products of each of these words, each of these adjectives, condition on the class. And then you need to do that for Y being positive, you need to do the same for Y being negative, and then you need to pick the one that gives us the highest probability. So if you do it for the positive class, the prior is 3 divided by 7. The probability of fantastic given positive is 1 divided by 10. Good given positive, it's 1 divided by 10. And lovely given positive is also 1 divided by 10. So you get this number at the end. If you do the same thing for the negative class, the prior that the class is negative is 4 divided by 7, but then neither of these words occur in examples that are negative, and therefore our estimates are that the probability are 0. Okay, so therefore we are going to predict positive because this probability is higher. So in fact, this model is telling us that it's impossible to generate such a document if the label is negative. So here's a second example. If you have this example, great plot, great casts, great everything, surprisingly for this data set, this prediction is going to be negative. And you can see that by doing all this computation. The reason why this is happening is that great actually occurs several times in negative reviews. So it occurs twice out of 8 adjectives. And it only occurs once in the positive class. So if you put together all these probabilities, actually it's more likely that the sentiment is negative. And finally, let's look at the last example. If you have these new documents, boring movie, annoying plots, unimaginative ending, if you use again our expressions, unfortunately, these words do not occur with either of the classes. So we never saw these adjectives before. So we are estimating a probability of 0 to them. And as a result, we are going to have a score of 0 both for the positive class and for the negative class. What should we do in this case? This is a problem, right? We have a tie. The model is telling us that this document is impossible. But it's not impossible because you are just seeing it. So the way of solving this problem is to do smoothing, which corresponds to do something similar to regularization. So instead of saying that things that are not observed at training time have probability 0, we are going to assign a default small probability to each of these events. And the simplest way of doing that is to do Laplace smoothing or add one smoothing, which is going to add a count of 1 to every event and then normalizing accordingly. So if you do that, then we will end up with a finite probability for both classes. And as a result, we're going to predict a negative sentiment for this example. So we are going to, I think this is one of the exercises in the lecture, in the labs this afternoon. So we are going to be able to play with this. And finally, the last thing before the break, and sorry for taking so long, you're probably very tired, is that the multinomial naive Bayes is an instance of a linear classifier. So everything is now tying together. And this is a one slide proof that shows that. So the naive Bayes classifier is predicting y that maximizes this quantity, which is a product of a prior probability with the class conditionals. Now, you can equivalently maximize the log of that. If we do that, we get the maximization of the log of the prior plus the sum of the logs of the class conditionals. And if we then call the log probability of the prior our bias term by, and if you call the log of the class conditionals the dot product between the feature vector that is computing the counts of every word, and our weights would be the log probability of each word given y, then this can be written as maximizing a linear objective like this, which is exactly how we redefine the linear classifier. So this shows that the naive Bayes model used for in this multinomial model, it's an instance of a linear classifier. Okay, so to recap, so generative models attempt to model inputs and outputs. This is what the naive Bayes assumption does. It estimates the joint distribution of x and y with the maximum likelihood estimation. The statistical model must explain the generation of inputs. So, interestingly, we can sample a document from the multinomial naive Bayes model by first using our prior to sample the label and then sampling a bag of words from the class conditionals. This is a good property of generative models. But we can also question if we need to model this joint distribution. If you only care about predicting y when x is given, maybe we can use a discriminative model instead. Maybe you don't need to model the input at all. Maybe you can just directly define a loss function that directly optimizes the conditional probability of y given x instead of bothering with modeling the generation of x. And this is what logistic regression does. It's something that we're going to cover in the second part. And perceptions and SVMs, they can also be regarded as discriminative models. And we are going to cover SVMs in the second part as well. So the only difference between generative and discriminative models is the way they are trained. At prediction time, they are both using, well, if we exclude perception, which is not probabilistic, but logistic regression, naive Bayes, they are both using P of y given x for prediction. We're going to clarify this in the second part. And this is it. There's just a couple of questions that I can answer before we go. Does the unbalanced data set will affect the naive Bayes model? Oh, that is answered already. Can you tell more about other smoothing techniques and their pros and cons? So I'm not going to add more details on smoothing, but in tomorrow's lecture, Noah Smith is going to talk a lot about smoothing in the context of sequential models. So he will tell you some more details. The kind of smoothing that I presented now is the simplest one you could think of. There's others that are fancier. There's also a question: doesn't naive Bayes return a probability distribution over classes labels if the probability of positive given W is K, probability of negative given W equals 1 minus K? I'm not sure I understand this question. Is this the prior probability? So naive Bayes, one of the things that naive Bayes computes is the prior probability for the labels, and that part actually, works for any generative model, not just for naive Bayes. And this is done by counting how often examples are seen in either of the classes. I don't know if this answers the question, but that's my interpretation about what you are asking. Okay, so I think we can do the break now. What time should we come back?
Maybe 11:20, maybe half an hour.
Okay. Do you need half an hour break? Maybe it can be a little bit shorter so that we don't go a lot over time?
11:15.
Okay, I guess 11:15 is okay.
Okay.
So see you in a bit.
Okay. See you.
All right, so I think we are ready to come back to the second part. All right, so here's a recap about what we did so far. So far we have covered the perception algorithm, multinomial naive Bayes, and we saw that both are instances of linear classifiers. We also saw that perceptron is able to find a separating hyperplane if it exists, and that naive Bayes is a generative probabilistic model. So next, we're going to talk about a discriminative probabilistic model. And so before that, just a reminder. So, we are working with a linear classifier, and this means that our predictions, y hats, are computed by taking the argmax of a linear function of this kind. So we have this matrix multiplication, w times feature vector phi of x plus a bias vector. And then you pick the class that maximizes this score. And so if you think about it, there is a key problem underlying how to obtain probabilities out of these scores. So this multiplication of w times phi of x plus b, it gives us a score vector that we can call z. And the problem becomes that of mapping from a set of scores to a probability distribution over y. We're going to see two mappings that do this. One is softmax, which is widely used. The other one is Sparsemax, that will appear later in the lecture. Okay, so let's move to logistic regression, which is associated with this softmax transformation. So let's recall that a linear model is able to give a score for each class by taking the dot product between the weight vector wy and the feature phi of x. I'm assuming that there is no bias. As we saw before, we can get rid of this bias by assuming that one of the features is constant. And as we have these scores, we can define a conditional probability by doing what is called the softmax transformation. So this means exponentiating these scores, and this exponential function ensures that the result is going to be positive. So there's not, the scores can be positive or negative, but once we do the exponential transformation, they will necessarily become positive. And then we can normalize them by dividing them by the sum of the exponential of the scores for all the classes. And this normalization ensures that the scores are going to sum to 1. Okay, so by construction, this transformation, which is called the softmax transformation, guarantees that we are going to obtain a probability vector. So something that is non-negative and that sums to 1 for all the classes. And so this is still a linear classifier. So obtaining the label y that maximizes p of y given x is the same thing as maximizing this expression that we used here, because the normalizing function does not depend on y. We can look at the expression for zx. It's a sum over all the y's, so it doesn't depend on a particular one. So we don't need to consider this denominator. So finding the y that maximizes this is the same as finding the y that maximizes the numerator. And because the exponential function is monotonic, this is also equivalent to maximizing the y, maximizing the score directly. So maximizing the dot product between wy and phi of x. Okay. Okay, so let's go back to the binary case first to cover binary logistic regression. So here the binary labels are either +1 or -1, and we assume that the scores are going to be 0 for the negative class, and the dot product between the weight vector w and phi of x for the positive class. Okay, so with this assumption, we can write the probability of the class being +1 given x to be the score of that class, which is exp of dot product between w and phi of x divided by the sum of the scores. If the class is negative, the score is 0. So the exp of 0 is 1. This is why we get a 1 here. And if the class is positive, then we get the same thing that we had in the numerator. And therefore, we can also divide both the numerator and denominator. We can divide it by exp of this argument. and you get 1 in the numerator and 1 plus exp of minus the score in the denominator. Okay, so here, the negative inside the exponent arises when we divide 1 by the exp, and the second term, if we divide the exp by itself, we get 1. So we get 1 plus exp of minus the score in the denominator. And this transformation is very common, also very common in neural networks, and it is called the sigmoid transformation. So we can regard the sigmoid as the binary special case of the softmax. And so geometrically, this is what the sigmoid is doing. So on the x-axis, we have z. This is our score. This is what we get by taking the dot product between the weight vector and the feature vector. And in the y-axis, we have the resulting probability. So if the score is very negative, the probability approaches 0, because the class -1 becomes more likely. If the score is very positive, then the probability approaches 1, because the positive class becomes very likely. And if the score is 0, then both classes have the same score, and therefore the probability of the positive class is 0.5. And the sigmoid comes from this shape that the curve has. So this is widely used in neural networks. Tomorrow Big Show is going to talk a lot about this. It squashes any score to a number between 0 and 1 that we can interpret as a probability. And this is always strictly positive. So the probability is never 0. It can approach 0 in the limits, but it's never going to be 0 or 1. And it's strictly increasing. So the higher the score, the higher the probability. Okay, so now let's consider the case where we have more than 2 classes. This is called multinomial logistic regression. And this is how we are defining the probability of each class. So one question that we need to ask is, how can we learn these weights from data? And the trick to do that is to set the weights to maximize the conditional log likelihoods of the training data. So unlike what we did with naive Bayes, where we were maximizing the joint likelihoods of the inputs x and the outputs y, here we are only going to maximize the conditional log likelihood, which means the probability of y given x. This is because x is observed, so we don't care about modeling the generative, the way the data is generated. We only care about, given the data, how to maximize the probability of the true class. And so to do that, we can write this optimization problem as that of maximizing the log of the products of the probabilities of yt given xt for each data point t. Okay, so we are assuming that the data is generated IID. And so maximizing the log is the same thing as minimizing minus the log. And then because we have the log of a product, this is equivalent to a sum of the logs. And plugging the definition of the probability that we have here, the log cancels with the exp, but we still have the denominator. And so the entire objective becomes this. Okay, so a sum for all the data points. And then for each data point, we have 2 terms. A term that I'm writing in red, that is the log of this denominator. And another term that I'm writing in blue, which is the log of the exp of the numerator, which is just the score, that can be written this way. Okay, so this is the score of the correct class, the score of the true class. And so the goal is to fit, to solve this optimization problem to fit the model to the training data. So intuitively, you want to set W to assign as much probability mass as possible to the correct labels. Okay, so one thing to note, I'm not going to give a formal proof, but it's that this objective function that I just wrote is convex. So if you have a linear model, this optimization problem is convex. And I think Mario talked a little bit about convex functions in yesterday's class. If our object function is convex, then this means that any local minimum of the function is also a global minimum. Okay, so this is good because we don't need to worry with initialization. So it doesn't matter how we go about optimizing the problem, as long as we are using an optimizer that is guaranteed to converge. The point that you're going to obtain is going to be the global optimum. So unlike naive Bayes, we don't get a closed form solution in logistic regression, but there's a lot of lots of numerical techniques for optimizing this objective that we can use. And this includes things like gradient methods, like gradient descent, conjugate gradient, stochastic gradient descent, and so on. And it also includes more powerful methods like LBFGS that you can use if, that are usually more effective in the small data regime. So if you don't have a lot of data. And so I'm not going to elaborate on that, but it's also possible to make a parallel between logistic regression and maximum entropy. So the two things are equivalent. So logistic regression is equivalent to maximizing entropy subject to constraints on features. So if you hear maximum entropy models, there is a connection between that and logistic regression. And this is a recap of convex functions. So they have the guarantee of giving us a global minimum. And in terms of optimization, this means that we can use iterative descent methods like gradient descent, where we start from an arbitrary point like this x0 here, and we do small steps in the direction of the negative gradients. And if we choose our step size wisely, this will eventually converge to the global optimum. Okay, so let's get back to the objective function that we are minimizing. We call this our loss function. It takes this form. Again, this red term that is a log sum exp, and the blue term that is just the score of the correct class. So you want to pick W, the matrix W, to increase the score of the correct class and to decrease as much as possible these other coefficients. And to solve that with gradient descent, we first initialize our matrix to all zeros, and then we iterate until convergence by performing gradient updates, okay, where we need to compute the gradient of this loss function with respect to W. Okay, so this implies having to compute the gradient of this full objective, okay? And because this objective, actually, so you need to compute the objective of the sum for all data points, all training points of individual loss functions like this. And because the gradient of the sum is the same thing as the sum of the gradients, then the gradient can enter the sum. Okay, so we just need to have a tool that allows us to compute the gradient of this loss function here. All right. So it turns out that we can, if you have a large data set, gradient descent can be very slow because before doing any updates on the matrix W, you need to compute this sum, which might mean summing over a very large number of data points. So this means that you need to visit every data point, accumulate all these gradients, and only after doing a full epoch over the training points, performing a gradient update. In practice, this does not scale very well if you have a very large data set. So an alternative is to do something called stochastic gradient descent, which approximates this gradient by using a single data point. So instead of computing this sum, you just sample a point randomly, and you only compute the gradient with respect to that point. And after seeing that point, you immediately compute an update on W. So this is like, you can regard this as a noisy estimate of the gradients. It turns out that this is an unbiased estimate of the gradients, because in expectation, if you have a uniform distribution to pick our example, in expectation, this corresponds to the true gradient. But it's noisy in the sense that this update is going to be highly dependent on the data point that we pick. But if you do this multiple times, many times, this method has very good properties. And in practice, it's very similar to what is used, in big data problems, either with the linear classifiers and neural networks. So there's also variance in between gradient descent, as I described earlier, and stochastic gradient descent, which you can use by using mini batches, which are particularly convenient if you are using GPUs, because we can parallelize the computation for these gradients. And so mini batches mean that instead of computing the gradient with respect to a single example, we have a small set of examples, which is called our mini batch. We sum only over the examples in that mini batch. We compute the gradient with respect to that. And then next time we get a different mini batch and we keep doing this. And for a suitable choice of learning rate schedule, this is all guaranteed to find the optimal choice of weight vector. So there is a question about, does the delta stand for subtraction? Where is the delta? Do you mean the nabla? So the nabla notation denotes the gradient. Okay, so we are going to derive the gradient of this loss function in the next slides. I think yesterday Mario talked a little bit about derivatives and gradients. So the notation that we are using here means the gradient of the loss. There is another question. If there are other options like SAG, SAGA, SVRG, yes. So there's many choices of optimization algorithms. I'm not going to cover them in detail. Some of them are particularly good if you don't have a very large data set. But even in the case where you have a large data set, there are variants of stochastic gradient methods that have better properties. There are ways of accelerating gradient methods. There's also techniques to introduce momentum. In neural networks, there are things like Adam and so on. Those things are going to be covered in the next lectures. Okay. So for this to work, we need to compute the gradient of the loss. So let's now see how we can do that. This is the function whose gradient we need to compute. We are going to use some reminders for that. The first is that the gradient of the log of a function, so f of w here is representing a function from a vector space, from the Euclidean space where w lives to the reals. So the gradient of that is going to be a vector of the same dimension as w. In this case, w is a matrix. So the gradient is going to be a matrix of the same dimension as w. If the gradient of the log of a function can be written as 1 divided by the value of the function times the gradient of the function. Okay, so this is a generalization of the formula for computing the derivative of log of x, which is which is 1 divided by x. Another reminder is the log of the exponents of f of w. The exponential of f of w can be written as the exponent of f of w itself times the gradient of the argument of the exponential. Okay, and we are going to use these two expressions in the sequel. We are also going to denote by ey the one-hot vector representation of class y. So if you have, let's say, 10 classes, this is a vector that is 0 everywhere, except in the entry that corresponds to the class that is indexing this vector ey. So this is the canonical Euclidean vector, if you want. So let's write the gradient of this expression. So we want to compute the gradient of this. It's convenient to separate these into a red part and the blue part. Because it's the gradient of a difference of two expressions, you can write it as the difference of two gradients. For the first part, we have the gradient of a log of something. So we can use the formula for the gradient of the log. It's one divided by that something, which is this sum, times the sum, times the gradient of the sum, and then the gradient of the sum is the sum of the gradients. So we end up with this expression in red. And the gradient of the blue part, it's the gradient of a function that is linear on wy, but in this particular expression, the gradient, so only the row corresponding to class y is being used. Okay, So the gradient with respect to any label that is not y is going to be 0. And therefore, we can write the gradient of this part as the outer product of the one hot vector EY and the feature vector phi of x transposed. So this is going to be a matrix, which is going to be number of classes times number of features. It's going to have rows that are all zeros for any class which is not y. And then for the class y, it's going to copy the feature vector phi of x. Okay, we can keep simplifying this expression. So you might notice that this summation here is just the normalizing function in the softmax, so zx. And now we have here the gradient of the exponential function. We can use the formula for the gradient of exponentials. It's the exponential itself times the gradients of the arguments. And if we keep doing this, then the gradient of the argument is very similar to what we did in the expression in blue. So, but this time we have a label y prime, an arbitrary label. So this becomes the outer product of ey prime with phi of x transpose. And now, the zx can also enter this sum. And by doing that, we will get this expression exponential of w dot product with phi of x divided by zx. And this is exactly the softmax transformation that defines the conditional probability of y prime given x. Okay, so this means that this entire expression in red becomes the sum for all possible labels y prime of the probability of y prime given x times this outer product, which you can regard as an expectation of this outer product. And so in matrix notation, we can write it this way. So this entire thing, because we are using phi of x in both terms, this entire thing is a difference of two vectors times phi of x transposed. And these two vectors are in red, the probability vector according to our model. So this is the output of our softmax transformation. And in blue, you have a one hot vector that indicates the correct label. So here's a quick summary of logistic regression. We first defined this conditional probability of y given x. And then we decided as a criterion to obtain the weights that maximize the conditional log likelihood of the training data. And we actually saw that we can find the gradients and just run gradient descent. And the gradient takes this form that we had in the previous slide. So the story so far looks like this. So naive Bayes that we saw in the first part is a generative model. It maximizes joint likelihoods. There is a closed form solution for naive Bayes. You just need to count and normalize. Logistic regression is discriminative. Obtaining an estimate of the parameters is a little bit more complicated, but not too complicated. We can still do gradient descents to maximize conditional likelihoods. It's also called the log linear model or the max entropy classifier in the literature. So if you see those names, this just means logistic regression. There is no closed form solution, but we can do stochastic gradient updates like this. Okay, and we also saw in the first half Perceptron, which is a discriminative classifier, but not a probabilistic one. We didn't talk about probabilities when we were describing the Perceptron algorithm. Instead, we focused on the Perceptron update equation, and that update equation looks like this, right? So we add if we are making a mistake, we add the feature vector for the row of the matrix corresponding to the correct class, and we subtract it for the row of the matrix that corresponds to the predicted but wrong class. Okay, and if the update is correct, these two things will cancel, and there is not any update. So wk plus 1 becomes equal to wk. But it's interesting to compare these two expressions for stochastic gradient descent with logistic regression and the Perceptron update rule, because they are really similar. So in fact, if we have a learning rate of 1, if eta is 1, then the blue term is exactly the same. In both cases, we're adding to the corresponding row of the weight matrix, we are adding the feature vector. And the red part is different but still similar. So in the perceptron case, we are just subtracting the feature vector for the row of the matrix that corresponds to the wrong class. In the logistic regression case, we are doing some kind of soft updates where we are taking into account the probability that the model is giving to each of the classes. But for example, if the model is very confident about a particular class, then this probability is going to be very peaked, and the update of logistic regression is going to be very similar to the perception update. So it's interesting to put these two things in perspective. All right, so this ends logistic regression. Now let's go back to the idea of separation margin that we introduced in the mistake bound for the perceptron. So recall that for a training set D, the margin of a particular weight matrix W is defined as the smallest gamma, such that the score of the correct class exceeds the score of any wrong class by at least an amount of gamma. Okay, so this is kind of the difference in scores between the true class and any of the other classes. We want a model that gives a big difference for all training examples. So we want gamma as large as possible. And the margin is defined as the smallest such gamma that is allowed by our training set and our choice of classifier. Okay, and so one criteria that might be interesting to consider is to try to, for the perception, we didn't care about finding a separating hyperplane that maximizes the margin. We were okay with any separating hyperplane, and the mistake bound in perceptron does not guarantee to find any optimal separating hyperplane. It just guarantees to find a particular one. But so now we are going to see that we can also use as a criteria the hyperplane that separates with the highest possible margin. So here are a few examples. Here we have a training set. We can pick any hyperplane classifier. At testing time, there's going to be some extra points here, and you don't want to have a lot of violations. A lot of points of the positive class outside this hyperplane, and the same thing for the minuses. And if you are given some training points, we might want to position our hyperplane in a way that maximizes this separation margin. And there's actually some theoretical good reasons to do that. There are some theorems that compute generalization bounds that are associated with the separation margin. Okay, so intuitively, maximizing margin makes sense. I was trying to argue in that direction. And this is the point that I was making about generalization error. I'm not going into details about that. Perceptron, is guaranteed to finding a separating hyperplane, but it doesn't care about maximizing the margin. So now we are going to talk about something called support vector machines, where we actually do care about finding a large margin classifier. So this is the problem that we want to solve. Okay, so we want to pick a classifier, let's call it U, and we are normalizing this classifier. So notice that because the decision that we are making when you are making a decision is an argmax, the scale of our weight matrix doesn't matter. If we multiply our weight matrix by some coefficients, this is not going to change our decisions about what is the class that maximizes the score, right? So we can, without loss of generality, we can assume that the norm of our matrix, where the norm of a matrix in this sense means vectorizing this matrix, like stacking all the rows together, forming a big vector, and computing the L2 norm of this vector. So without loss of generality, we can just assume that we are sticking with the models that are normalized, and you want to maximize the separating margin gamma. But you want to satisfy the properties of margin, right? So we want that the score of any correct label exceeds the score of any incorrect label by an amount at least gamma. And we are assuming here that the data sets are separable. We are going to consider later the case where they are not separable, but for now, let's assume that they are separable. And of course, the solution is still guaranteeing a separating hyperplane. In particular, it's going to pick the one that maximizes the margin. So there is a question, what happens to the classification of the values inside the margin? Okay, so this is a great question. I'm going to answer it here. So if at test time a point falls inside the margin, so let me go back to the previous slide. So if at test time we have a point, like for example these ones that are inside the margin, then the classifier is doing what is expected. It's going to use the right side of the half space to assign a label to those points. So in this case, it will still give them labels plus for this case because they all fall on the region of the space that is associated to the positive class. But in this case, the margin will be smaller than the one that was observed at training time. So the margin is a criterion that is used at training time, but at test time, there might be points that fall inside the margin, and the classifier is still the same as the linear classifiers that we saw earlier. So they will still decide one thing or the other, depending on which side the point is on. There was also another question, the softmax output of a perceptron for multilayer perceptron is often equated with the certainty of the model's prediction. If perceptrons aren't probabilistic models, are such claims actually incorrect? I'm avoiding relating here these probabilities with model uncertainty because I'm not going to get into details here, but especially with neural networks, models tend not to be very well calibrated. So they, it might not be a very good assumption to assume that the probabilities they return are related to their uncertainty. There are other methods that try to quantify this uncertainty, with better guarantees. But the way I define perceptron here was not in any probabilistic way. Okay, so sometimes people talk about multilayer perceptron in a broader sense. For example, assuming that sometimes you see something that refers to any linear classifier as a perceptron classifier. In this talk, I'm a little bit more strict. To me, perceptron is just that particular update, and that particular update does not convey any probabilistic meaning. It just gives you a score. You just decide on a prediction, a class based on that score, and you don't need to have any probabilistic semantics there. If you are using a softmax interpretation, then this is because you are probably doing something closer to logistic regression, where we are applying a softmax transformation to convert your scores into probabilities. All right. Okay, so going back to the point where I was. Okay, so this is the problem, the optimization problem associated with maximizing margin. Now we are going to do some small modifications to this problem that are going to result in an equivalent problem, but something that is more amenable to solve by an optimization algorithm. So the first one, this is already explained. So we are fixing the norm of the classifier because scaling U is trivially going to produce a larger margin. If we scale the magnitude of the classifier, by the way we are defining it, the difference of these scores is going to increase. But this is very artificial. This is why we need to impose that the classifiers are normalized. And now we are going to do some transformations. Okay, the first one is that maximizing the margin is equivalent to minimizing the norm. And let me be more explicit about what that means. So instead of normalizing U, we could not normalize U. We could work with a normalized W. But instead of having gamma here in this inequality, we could fix the norm. So instead of fixing, you could fix the margin. So instead of fixing the norm of the classifier and maximizing the margin, we can fix the margin, say that the margin needs to be 1, and minimize the norm of the classifier. The two things are equivalent. You can notice that by making a substitution, defining W as U divided by gamma. By doing that, we obtain the equations in the right. And these two optimization problems are exactly equivalent. Okay, so now we have a nicer problem that consists of obtaining the W that minimizes the norm, the L2 norm, subject to these constraints that states that the difference between two scores between the correct class and any incorrect class is greater than or equal to 1. And now, because we have a quadratic objective and we have a linear constraint, linear on W, this is an instance of a quadratic programming problem. And for those of you who have who know something about optimization, you might know that the class of quadratic programming problems is a nice convex optimization problems, and there are many solvers that are good at solving these problems. So we could immediately plug these into a solver, off-the-shelf solver, to get to fit our model to the data. There is a small twist here. So far I've been talking about the case where the data is separable, but in general that does not happen. For a real-world problem, the data is oftentimes not separable. But you still want to do some sort of regularization so that we find an hyperplane that approximately separates the data, or it separates as much as it can, but it might allow for some slack for points that cannot be separated. And so one way of accounting for that is to add this regularization term. And instead of requiring that the margin is greater than 1 for all points, we define it as 1 minus psi of t, where psi is a slack variable required to be positive. And we penalize the amount of slack in our objective function. Okay, so this is allowing for some margin violations, but we penalize those violations in our objective. And so this new objective function is able to handle data sets that are not separable. But now we have two variables. We have W and we have psi. And notice that this is still a quadratic problem because the objective is linear in psi, and linear is a particular case of quadratic. And this constraint is still linear in psi. So historically, SVMs and kernels co-occurred together. So the first versions of support vector machines were an example of kernel methods. And they were extremely, this combination of SVMs and kernels, they were extremely popular. This happened in mid-90s. Actually, we can kernelize other algorithms beside SVM. So there is nothing special between kernels and SVMs. We can use kernels in any other things like logistic regression, perceptron, and all these algorithms have also been kernelized. I'm going to talk a little bit later about kernels if time permits. So going back to the SVM's objective, this is where we are right now. This is our problem. And so instead of adding one constraint for every possible class, any possible incorrect class, any possible y prime that is different from the correct class yt, one alternative to say that the score of the correct class needs to be bigger than any of the other incorrect classes plus a margin for each class is to say that it needs to be bigger than the maximum score for each class for the most violating example, right? For the most violating class. And so we can write that using the max function here. And now if we rearrange the terms in this inequality, we can also write psi t greater than or equal to 1 plus this maximization. Okay, and in fact, because we are penalizing these psi t's, and psi t's are constrained to be positive, the best that we can do is to have them equal to this expression and not greater than that. So we can replace this greater than or equal to an equality. And if you do that, also doing another transformation. So here we had a C coefficient that controls the amount of penalty that we are giving to these margin violations. We can divide the entire thing by 1 divided by C, and we can call 1 divided by C lambda. And by doing that, we can equivalently scale the objective and have a sum of the size plus lambda divided by 2 times the square norm of W. Okay. And so if you do that, and if you realize that the best we can do is to have psi t equal to this, then we can replace psi t in the objective and get rid of the constraints. Okay, and by doing that, we obtain something called the Hinge loss. So the Hinge loss is the term that corresponds to summing all the xi's where the xi's are defined as 1 plus this maximum, which is the same thing as the maximum between 0 and 1 plus the maximum for the most violating class, white prime, of this expression here. So in other words, SVMs are optimizing this loss function with some regularization that corresponds to this term here that minimizes the margin. So this is the Hinge loss equivalence for the problem that we are optimizing. And you might notice that since this is taking the maximum of linear function of W, this is going to be a piecewise linear objective. So the Hinge loss is a piecewise linear function. And it's not going to be differentiable everywhere. So we cannot use gradient descent as we defined earlier, but we can use something called subgradient descent. I'm not going to get into details. The main message to keep in mind here is that subgradients are a generalization of gradients that allows to run algorithms similar to gradient descent, even if functions are not differentiable, but are convex. And we have an efficient way of computing a subgradient for the Hinge loss, which allows us to do updates to obtain the parameters of support vector machines. And I'm skipping the mathematical details here, but a subgradient of the Hinge loss can be written in this way. So it's a difference of two terms, which are very similar to the perceptron updates. So one of the terms is the row of the matrix corresponding to the correct class, and just copying the feature vector to that row and having zeros everywhere else. The other term is the same thing, but instead of being the correct class, it's a class y hat, where y hat corresponds to this maximum here. So it corresponds to the class, not the class that the model predicts, but something like a cost augmenting prediction, where we are adding 1 to all classes that are incorrect and keeping the score of the correct class, which we can represent here with this notation here. So maybe this is a little bit more clear if I put everything in perspective. So with the perceptron updates, our updates look like this. So if the model does the correct prediction, which is this first condition here, there is no update. So the delta of the weights is 0. If there is a mistake, then the y corresponds to the prediction of the model. It's the class that maximizes the score, and the update becomes a difference of two terms, which are copying the feature vector to different rows of the weight matrix. In the case of the SVM, it's very, very similar. The things that change are the prediction is 0, not necessarily if the model makes the right prediction, but if it makes the right prediction with a margin at least 1. Okay, so if it does the right prediction with a margin at least 1, there is no updates. If the margin is smaller than 1, or if the prediction is wrong, then we need to predict the most violating constraints, which corresponds to the point y that maximizes this objective. And this is the y that is going to be used in these updates, which really look like the perceptron condition. So in a nutshell, the perceptron is like SGD with a no margin Hinge loss. Okay, so here's a summary of what we have covered. We covered linear classifiers, including naive Bayes, logistic regression, perceptron, and support vector machines. Next, we are going to talk briefly about regularization, softmax and Sparsemax, and nonlinear classifiers. So let's start with regularization. So this was the slide I had in the beginning when I was describing underfitting and overfitting. So the main idea is that if the model is too complex, if there are too many parameters, and we have little data, then we run the risk of overfitting. This is what happens in regression if we have a very large degree for our polynomial, for example. We also saw an example of that in naive Bayes. If we don't smooth in naive Bayes, there's going to be some words that we never observed at training time, or that we observed very rarely, and you might have very inaccurate probabilities estimated by naive Bayes. So in practice, what we do is to regularize the models to prevent overfitting. And one way of regularizing is to, instead of just minimizing a loss function, minimizing a combination of a loss function with a regularizing term that I'm denoting here by omega. And normally this regularization term does not depend on the data. It just depends on the model. So we can see it as some kind of prior that we have about the model. And we have a coefficient that I'm denoting here by lambda that controls the amount of regularization that you want to give. And typically we optimize this, we treat this lambda as an hyperparameter. So we use some kind of validation set where we try different values of lambda. And when we are happy, when we get the best performance in the validation set, then we use it as our final model. Sometimes we do things like cross validation, k-folds, cross validation, and so on. I'm not going to discuss that here. But yeah, so the message here is that we typically need to balance how much the model fits the data with how complex the model is, or and this complexity is controlled by this regularizer. And we already saw one example when we called about L2 regularization for regression, which corresponds to a Gaussian prior. So this corresponds to having the L2 norm of the weight matrix W. So basically summing all the squares of all the weights. This is penalizing weights that are too large. So this is pushing the model for having smaller weights. Another choice that is very used in widely used in practice is using the L1 norm instead of the L2 norm, which corresponds to using a Laplacian prior, if you want a probabilistic interpretation. So this corresponds to using the L1 norm, which is the sum of the absolute values, instead of the square of the L2 norms. The effect of this norm, I'm not going to talk about that here, but this norm encourages weights to become sparse. So this means that many of the weights of the model are going to be encouraged to be exactly 0. And if a weight is exactly 0, since we are defining the decisions by multiplying weights by the feature vector, this has the effect of ruling out features completely. So we usually it's convenient and it's commonly done to use L1 regularization as a method for feature selection, because if you end up with a weight of 0, then we can just eliminate completely the feature from our model. So this is a simple picture that illustrates the points with the trading of model complexity by fitting the training data. Take this with a grain of salt. So this this picture, this analysis, it makes sense for linear models. In neural networks, there's a lot of ongoing research that challenges this assumption. And if you look for things like double descent curves and generalization in neural networks, you will see a lot of recent work that shows that models can have a lot of weights. They can be overly parameterized. They can overfit, but still have good generalization capabilities. But I'm not going to get into those details here. So in the simple story, there is a trade-off between how complex your model is and how well it generalizes on the test data. So what we often see is that as you make your model more and more expressive, for example, as you increase the degree of your polynomial in regression, your error in the training data is going down. It might eventually become 0. But after some point, the error in the test data starts growing because we are just overfitting the training data and we are not generalizing well to the test data. And so the goal is to find a good sweet spot where the training error is small, but the error on the test data is not increasing. So the simplest way of doing that is with L2 regularization, which is what I'm going to talk about now. So it's very easy to add L2 regularization to logistic regression. We just need to add this extra term that penalizes the norm of W. And of course, if you change the objective function like this, we need to compute the gradient also taking into account this regularizer. But the gradient of this L2 norm is actually super simple. You know, the sum of the gradients the gradient of this objective function that considers both the logistic regression loss plus the regularizer involves, since it's the sum of two terms, is the gradient of the loss that you already saw plus the gradient of the regularizer. And the regularizer is a squared L2 norm times a constant lambda. So, you know, there is a very simple expression for computing this gradient, which is just lambda times the matrix itself. Okay, so this is a generalization of the fact that the derivative of 1/2 x squared is x. So this is good. It means that we can immediately plug this in our stochastic gradient descent or gradient descent updates. It actually corresponds to something called weight decay. So if you ever heard of weight decay, this is the update that we get if we do L2 regularization. In SVMs, it turns out that L2 regularization is already happening with the description that I gave so far. So the objective function of SVMs already contains, you know, lambda divided by 2 times the L2 norm squared of W. And the reason why it contains this term is that this term is used to maximize the margin. So the meaning of this term is actually to maximize the margin. And therefore, you know, it's already built in SVMs, this L2 regularization. And so this is how SVMs compare with logistic regression when we are regularizing both. They both have a regularization term of this kind. The only thing that differs is the loss term. In SVMs, the Hinge loss is of this form. In logistic regression, we use something called the log loss, which is of this form. So in general, we might be asking, we saw a lot of loss functions today. If I have a new problem, which loss function should I pick? And this is a hard question, you know, so the loss function should match as much as possible the metric that we want to optimize at test time. It should also be well behaved. So it should be continuous. It should be maybe smooth if you can, so that it's amenable to optimization. And so, for example, this means that the 0-1 loss is not a good choice. The 0-1 loss is the loss where if you get the right class, the loss is 0. If you get the wrong class, the loss is 1. Because this loss function is discontinuous. You cannot compute gradients throughout this loss function. And there's many hardness results when you try to optimize this loss directly. And so some examples of well-behaved losses include the squared loss for regression, the negative log likelihoods, or also called the cross entropy loss, which corresponds to multinomial logistic regression, as we saw before, the Hinge loss associated with SVMs. And next, we are going to talk about another loss called the Sparsemax loss that can be used for multi-class and multi-label classification. So before that, there is a question in chat. So now we have to choose lambda. Yeah, so lambda is typically chosen as an hyperparameter instead of being a parameter as W. And you know, the typical choice for that is to define a validation set, try out a range of different values of lambda, doing grid search to obtain to try out different lambdas, and look at accuracy in the validation sets, and then pick the lambda that leads you to the best trade-off, and then use it and evaluate the model on new test data when you already trained the model with that lambda. There are alternative techniques that try to learn to learn. You know, there is a big area in machine learning about learning to learn, which involves learning hyperparameters, including some coefficients like regularization coefficients like lambda. But you know, there is in general, you know, there is no magic way of getting us the lambda automatically. Okay. Could you explain what you mean by well-behaved? So this appears in the context of losses. Yeah, so by well-behaved, I mean a loss that allows us to do gradient descent to optimize. So this rules out the zero loss because it's discontinuous. The gradient is going to be zero piecewise. So if you perturb your matrix W a little bit, infinitesimally, then your decisions are not going to change, and therefore the gradient is going to be zero almost everywhere. And therefore, you cannot learn a model. You cannot fit W with gradient descent methods using optimization techniques if you want to optimize losses like that directly. And there's other losses that are also discontinuous that are not very good choices. So the ones that I'm listing here in these bullet points, they are all well behaved in the sense that we can either compute gradients or compute subgradients, which allows you to do gradient-based optimization. All right, so so let's move on to a slide that I had in the beginning. Recall that when we talked about logistic regression and we talked about the softmax transformation, our key problem was to map from a set of label scores, a vector Z with a score for every possible label, where these scores can be positive or negative, into a probability distribution over the labels, a probability vector over the labels. And softmax is a way of doing that. Now we're going to look at another possibility called Sparsemax. So, first, let's recap that softmax, what it's doing, it's just exponentiating every coordinate of the vector Z and normalizing. And by construction, this is going to ensure that this is going to result in a valid probability vector, a vector that is strictly positive and sums to 1. One thing that is also going to happen is that because the exponential function is strictly positive, it's never going to return 0. We are never going to have 0 probabilities for any of the labels, which is fine for many problems. But if you are working on a problem for which you want to select things, problems for which you really want to have 0 probabilities for events that are impossible, then we cannot use softmax for that. I mean, the way to do that is to define a threshold and say that if the probability is less than that threshold, let's make it 0, and then let's renormalize everything to sum to 1. But it's a little bit of an heuristic. So there is an alternative transformation called Sparsemax, which we proposed in our group. That is a sparse-friendly alternative to softmax. I'm just going to very briefly convey the main idea and skipping the mathematical analysis. So the way Sparsemax is defined is you have your vector Z, your score vector, and you want to obtain a probability vector which lives in this space, which is called the probability simplex. I'm using this triangle here to denote the probability simplex. This is the set of valid probability vectors. It's the set of points that sum to 1 and are all non-negative. And so one way of mapping from Z to P is by doing an Euclidean projection of your score vector onto this probability simplex. It's by construction, it's going to return a valid probability vector. And it turns out that these Euclidean projections onto the simplex, they have a tendency to be sparse. I can, if you are not convinced by why they are sparse, I can give you some more explanation later if you ask that question. So these explanations tend to be sparse, and this is where the name is coming from. And a bit surprisingly, when we come up with this, we found out that Sparsemax, despite being defined in a very different way than softmax, it actually retains many of the properties of softmax. For example, it's still differentiable almost everywhere. So if you perturb the scores a little bit, your probabilities are also going to change a little bit. And we can actually compute gradients, and it's efficient to compute them. And doing this computation to obtain the vector P, can be done in a very efficient way in linear time by using a specialized algorithm. So there is a closed form for this softmax that corresponds to subtracting a constant from every coordinate. And the problem becomes that of getting the right constants that ensures that we get normalization in the end. So I'm going to skip the mathematical details, but just give you how geometrically this looks like. Earlier, we saw that softmax in 2D corresponds to the sigmoid function So in 2D, we can, without losing any generality, we can assume that one of the labels has a score of 0, and you only worry about having the score for the other label. And we can compute the probability of that label with the softmax transformation. If we do that, we get the sigmoid, which is this line in blue, right? So it's a curve that saturates between 0 and 1, but it's never 0 and never 1 because of the positiveness of the exponential function. The Sparsemax has a similar asymptotics, but it's like a hard sigmoid. So it's going to result in a piecewise linear function where if the score is very negative, it's going to become 0. If the score is very positive, it's going to become exactly 1. So it's not asymptotically, it's really going to achieve exact zeros and exact ones. And in 3D, you have something similar. So in that case, softmax is this smooth surface here, and we get something that is piecewise linear that corresponds to Sparsemax. And if we prefer to reason about probability vectors, if I pick a random score vector z like this, where a few components are positive, others are negative, if I apply the softmax transformation, I get these bar plots. So this is assigning probability value to each of these 5 classes, and everything sums to 1. On the other extreme, if I do the argmax, then argmax is just going to give a 1-0 vector with which only has a 1 for the class with the maximum score, which is the first one. And Sparsemax does something in the middle. So it assigns 0 probability to everything except the first class and the fourth class. It turns out that this transformation is, besides being sparse, it's also differentiable. So we can, in any place where you use softmax, you can also use Sparsemax. And if this is something that you are interested in, let me know. We have some software that makes it really easy to experiment with this, both in linear models and also in neural networks. Okay, so we can also use Sparsemax as a loss function, as an alternative to cross entropy, which is what we do in when we use softmax. A caveat is that Sparsemax is sparse by definition, right? So this means that we can get probabilities of 0, and we get the problem if we take the log of those probabilities of 0, because log of 0 is minus infinity. So we cannot use Sparsemax, or at least it's not a good idea to use Sparsemax and maximize log likelihoods. We need to have a different loss function if you want to use Sparsemax. And without going into a lot of details, the right loss function is one where the gradients of the loss are really similar to the gradients of softmax, which means that if you're using something like stochastic gradient descent for multinomial logistic regression, you can replace your output layer by Sparsemax, and you can still compute gradients with a similar expression just by replacing softmax by Sparsemax in your gradients. And the loss function that corresponds to that, it has this strange expression. It is a particular case of something more general called a Fenchelian loss. I'm not going to explain what that is, but it's kind of a natural choice with very nice properties, including convexity, margin, and so on. That goes really well with this Sparsemax transformation. Okay, so putting everything together for the binary case, we have covered all these different loss functions in this talk. The one in red is the 0-1 loss. It gives you a loss of 0 if you get the correct class, and a loss of 1 otherwise. So the x-axis here is the score function, or minus the score function, to be more precise. So if the score is negative, this means that the decision, if minus the score is negative, it means that we did the right decision. Otherwise, we did the wrong decision. All the other losses are kind of losses that are more well-behaved, more amenable to optimization, that try to serve as surrogates for this 0-1 loss. So we covered the logistic loss, which corresponds to logistic regression. This is the line in blue. This corresponds to the log probability. We also covered the Hinge loss, which corresponds to SVMs. And this takes this piecewise linear form. It's 0 if the score is bigger than 1, which means that we are giving the right classification with the unit margin. and then it starts to get penalized linearly. We cover the perceptron loss, which is similar to the Hinge loss, but without a margin. So this is the purple line here. And we very briefly cover the Sparsemax loss, which is the green line here. And the Sparsemax loss happens to also have a margin, just like the Hinge loss, but it doesn't have this discontinuity. It doesn't have this non-differentiability of the Hinge loss. So it's something that is differentiable everywhere. And you can also see it as a rotation of the squared loss. It's also, sorry, it relates to the squared loss for classification, and it can be regarded as a form of the Huber loss for classification. Okay, so this finishes the part about regularization. How much time do I have? So I think this lecture is supposed to finish at noon 30, but we started a little bit later. I think we might be able to start to finish either on time or not very far from the time where it was supposed to. So let's talk a little bit about nonlinear classifiers. So just to recap, this is what a linear classifier can do. It can separate, well, if we are not regularizing, if you want to have a exact separation, then a linear classifier can do well on problems that are linearly separable, things like OR and AND. But it cannot do well with XOR functions. If things are not exactly separable, but they are almost separable, we can regularize a little bit and you can still get good performance. But if things are, strongly non-separable, like this XOR example here, then there is no hope that a linear classifier working in that feature space is going to do well. So the only thing that we can do here, if you want to stick with linear classifiers, is to modify your feature space, is to do feature engineering to represent our features in a different way, to move things to a space where things are separable. And this is what we do if we modify our inputs to be, instead of x1 and x2, to be negated x1 and x2 and x1 and negated x2. In that case, the circle points collapse and everything becomes separable. So there is a question in the chat. Sparsemax looks interesting. Is it available in PyTorch? Yes. So it's available. I can write the link here. So so there is a project called Entmax that we have in our group repository that implements something a little bit more general than Sparsemax, that considers Sparsemax as a particular case. And all those transformations are sparse. So if you want more details, you can chat either in Slack or in email, and I can give you some pointers. All right. Lost my slides again. Okay, give me a few seconds to recover them. So actually, if you do pip install Entmax, you can start playing with this transformation. Okay. Okay, I got my screen back. So yeah, so we saw that linear classifiers cannot, separate problems that are strongly non-separable unless we transform the features. But maybe there are other things that can be done. So, and we are going to see that in a little bit. All the linear classifiers that you saw so far, they lead to convex optimization problems. So we don't have any issues with local minima or initialization. And they all assume that features are already engineered. So we are not explaining how to engineer features. We assume that there is already someone in the team that knows how to do that. We just get the data already in a form that is nearly linearly separable. But of course, in practice, that's not always the case. So what to do if data is not linearly separable? There's a few possible strategies. Well, we can engineer better features, and this looks very naive, but it often is the best choice. Or we can do something called kernel methods, where instead of worrying so much about the feature space, we define a similarity function. that defines similarity between different inputs, and implicitly, this is doing some computations in some high-dimensional feature space that we don't care about. I'm going to talk a little bit about kernels in the end, but this doesn't completely solve the problem. So here we don't need to engineer features anymore, but you still need to choose a good kernel or to design a good kernel, which is not trivial either. And our model capacity is still confined to positive definite kernels. So kernel methods are not as expressive as neural networks. So the other possibility, which is going to be covered in Diksha's class later today, is using neural networks, where we just forget about trying to get something that is convex. You just embrace non-convexity. We are okay with local minima. And instead of engineering features and kernels, you still need to do some engineering, but it's different kind of engineering. You need to worry about the model architecture, like how many layers it's going to have, how many input units, how many hidden units, if we are using RNNs or transformers and so on. And this is something that it's going to be the topic of other classes as well. All right, so there is another question. Can you say anything about the difference between the problem of determining whether there is a linear separating hyperplane and the problem of finding one? Yeah, so in general, like I cannot state the complexity results. I know that there's many papers that look into that in the more theoretical angle of machine learning systems. In general, the punchline is that it's also very hard to identify if there is a linear separating hyperplane, if you have like a big data set and very high dimensional features. Of course, in 2D, it's very easy, right? I can just plot the points and visually we see if the data is separable or not. But if you want to do this in high dimensions, it's not as easy. Of course, you can try, if you want to do this empirically, you can, if you have like a budget of time in which you can try to do that, my advice would be try to implement something really simple like a perceptron, which is probably the simplest thing we can think of. If you see that perceptron is struggling, that means that probably your data is not linearly separable, and it's very far from it. If the perceptron is already doing well, then maybe you don't need to worry more about that and just invest in something a little bit better than the perceptron, like SVMs or logistic regression or Sparsemax, and not worry about the features. All right. Okay, so in general, there are two views of machine learning. So there's two big ways of building machine learning systems. One is feature-based, which is what we have been doing so far. In that case, what we do is we have a bunch of objects that we want to classify. And to classify those objects, we are going to describe their properties, which means we are going to come up with some features. And this is basically what we have seen so far. Neural networks, what they do is instead of requiring us to describe those features, they have a way of discovering good internal representations that represent objects' features themselves. The second way is instead of describing objects' properties, we write a function that tells us how similar, that quantifies how similar two objects are to each other. And this is a very interesting perspective, right? Philosophically, these two things are highly complementary. So instead of describing, enumerating all the properties of objects, which can be, many properties and many very complex ones, we only assume that there is a function that gives us a number. That's when you pass like a pair of objects to this function, it gives us a number that tells us how similar these two objects are. And when we are doing things like nearest neighbor classifiers, we are doing something like that. So in nearest neighbor classifiers, our training data is memorized. And then if we have a new example, what we are going to do is to look for the examples that we have seen at training time that are the most similar to this one. And when we identify the kth most similar examples, we are going to look at their labels, the ones that we have available at training time, and we are going to use some voting or something similar to predict a label for the new example. Kernel metrics do something similar in a more sophisticated way. And Gaussian processes are another instance where we do this kind of stuff. But so interesting, sometimes this feature-based perspective and the similarity-based perspective are equivalent. And there is very beautiful theory around it. So this is what I was saying before for nearest neighbor classifiers. It's not a linear classifier. It can build an arbitrarily complex decision boundary. In the simplest version of nearest neighbor classifier, we don't need any parameters, but we need to remember all the data that we have seen at training time. And so computationally, we need to come up with a good way of storing that data efficiently and how to search over that data. So it memorizes all the data. Given a new point, we retrieve the most similar data point, or the case most similar points. And that's how it works. It can also be very effective in practice. So this is also, if you are working on a new problem in some company, the two things that you should start experimenting with are the Perceptron and the nearest neighbor classifier, because they can be already very strong baselines. And if they are not, they will tell you something about how good your features are in the case of the Perceptron, or something about how good your similarity function is if you are doing nearest neighbors. So one way of encoding these similarity functions is by using something called a kernel function. So a kernel function is a similarity function between 2 points that has this additional property of being symmetric, meaning that if you are comparing a point A to a point B, you get the same number if you compare point B with point A. And the second property is that it should be positive semi-definite. And this is a more complex definition, but it means that if you collect your training sets and you compute your gram matrix, this is the matrix where each entry is the kernel value that compares the pair of elements indexed by the row and column of the matrix. So it's a matrix that is n by n, where n is the number of examples in the training set. So if you have this gram matrix, then any gram matrix that you can construct with arbitrary training sets needs to be positive definite, which means that it satisfies this property for any vector v, Okay. So if this happens, then we say that this kernel is positive semi-definite. And there are some nice closure properties of positive semi-definite kernels. And there's also a very nice theorem that establishes an equivalence between these similarity-based methods based on kernels and feature-based methods. So this is a theorem due to Mercer. There are many versions of it. It states that for any positive definite kernel, on an arbitrary space X, there exists some feature mapping phi, that can be arbitrarily high dimensional. It can have infinite dimensions. So we're not stating what the features look like, but there is some feature mapping such that the kernel function applied to these 2 points is equal to the dot product between the feature vector of xi and the feature vector of xj. And so usually we don't care about the explicit features. We just care about the kernel. And there are many ways of kernelizing algorithms. So kernelizing here means taking an algorithm that works with features and writing a version of this algorithm that is equivalent and works with kernels. And if you do that, then we never need to instantiate features. We can only compute kernels along the way. And kernels are also well studied. So because of these nice closure properties of kernels, there are ways of combining different kernels to build a new kernel and doing things like that. So this was an extremely popular idea in the 90s and 2000s. It fell a little bit out of fashion today with the with the success of neural networks. There are still there's many people that are studying kernels in the scope of neural networks. There's something called the neural tangent kernel that is like a way of understanding the dynamics of neural networks. So I think there's there's still very active research directions using kernels, but they are less mainstream. So from a practical perspective, one of the obstacles of kernels in problems that involve large data sets is that you need to either store these metrics with all the similarities between all pairs of examples, or we need to do computation that involves at test time comparing your example with a large number of examples in your training sets. And this is often not appealing for many problems in practice. So in many cases, it's still preferable to use features. But it's interesting also to understand how these things connect to each other. So kernels offer us a way of developing classifiers that are not linear in the original space, because you can transform our points to a feature space by using this kernel function, where things are linear in these features, in this new feature space, but they were not linear in our original space. So for example, if we start with a problem in 2D that involves separating the minuses from the pluses, we cannot do that with a linear classifier, but we can define a kernel function that corresponds to in this case, a 3-dimensional, but it can be arbitrarily I-dimensional feature space that we don't care about because you never compute there, such that there is a linear hyperspace in that feature space that when we project it back to this feature space becomes a parabola like this. So this is a very pictorial example, but in practice we can define more complex, separating boundaries by using this idea. So this is the same example, a similar example where we have points defined like this. So we have like one inner circle with one class, and then we have like another circle. These blue points are surrounded by red points. There is no way a linear classifier can separate the two. But if we define a smart projection by using a quadratic kernel function, these things become very easy to separate. In this case, in 3 dimensions. So this was an instance of a polynomial kernel. So this example in this slide is achieved with a polynomial kernel of degree 2. So here the transformation function, the kernel function, is defined. This is the actual feature representation. The kernel function is defined by, sorry, what happened? So the kernel function is defined by taking the dot product and add a constant and square it. Other popular kernel that is widely used is the Gaussian radial basis kernel, which defines a distance between 2 points and squares this distance, scales it, and then feeds it to the exponential function. And there is a relation between that and Gaussian distributions. There's also kernels that have been defined for data that is not originally in a Euclidean space. For example, kernels between strings, between sequences, or kernels between trees. There's also kernels between graphs. And these things have been used in several natural language processing problems in computational biology, and so on. There is a question: what does the kernel trick offer an advantage versus calculating feature engineering vectors? So the advantage is, it doesn't always offer an advantage, but for problems where it's not intuitive how to design good features, and where it's more intuitive to define how 2 examples are similar to each other, then the kernel trick, avoids having to understand what characterizes the properties of these objects. And we can just work directly with kernels. It's also possible to use the reversed kernel trick, and I've seen some instances that do that recently. So this happens in problems that, for some reason, there is something that can be characterized as a kernel that compares, two vectors or 2 objects, and we want to approximate this kernel with a feature representation, and then we can actually compute using features. So there's many stochastic ways of doing feature approximations of kernel functions. We even see that in recent work that tries to make transformers more efficient, where people are using something similar to this kernel trick, but in a reverse manner. How do you search for the right kernel? Yes, so this is a very tricky question. There is no free lunch. It's not possible to. There are many methods that try to learn an optimal combination of kernels. There is a lot of work on something called multiple kernel learning that used to be a very popular line of research in the beginning of the 2000s. because it takes advantage of the fact that kernels are closed under convex combinations. So this means that if you have several kernels to start with, any convex combination of these kernels, meaning any linear combination where the linear coefficients are positive, this is actually a conic combination. So any combination like that is also a positive definite kernel. And there are algorithms that try to learn those coefficients using convex optimization. Those things are very interesting. But I think they kind of eat an obstacle in how much improvement they can give. So in practice, the problem of searching for a good kernel is also not easy. Visualization can help for sure. All right. Okay, moving on. Lost my screen again. Sorry about that. So every time I see questions in chat, when I type ask, accidentally I lose my screen. Okay. Okay, so so just before we finish, I'm going to cover something that I didn't cover in the talk, but I think it might be useful for the labs this afternoon, which is the concept of joint feature mappings. So for multi-class or structural classification problems, sometimes people use something called joint feature maps, where features are not only depending on X, but they depend both on X and Y. So I'm denoting that by psi here instead of phi. So psi of X and Y depends on both the input and the class. So each feature now represents a joint property of the inputs and of the candidate outputs. So an example of that, if X is a document and Y is a label, one feature could be a feature that is binary, and is one if the document contains the words interest, and the class is financial, if we are trying to predict the topic of the document. Another example could be the percentage of words in the document that have punctuation, and the label being scientific, and so on and so forth. So this is basically a conjunction of something that depends on the inputs and the label. Other examples like X being a name and Y being a label that classifies the type of entity, if it's a location, a person, and so on. And you can combine every feature on X with every label on Y. So if we associate a weight to each of these features, we're going to end up with the number of weights that is exactly equivalent to the weight matrix that I have showed you before. And so these feature vectors are usually defined in blocks. So if there is an actual document and we are hypothesizing an actual label, like person, for example, all features that correspond to labels that are not person are going to be zeroed out, and features that correspond to that label and each of these words are going to have an entry, corresponding to the features that we have defined. So the non-zero values are allowed only in one block. And if you want to make a parallelism between the feature representations that we have seen before, that we called phi of X, the features that depend only on the inputs, we can characterize these joint input-output features as some kind of Kronecker products between the feature vector that we had before and the one hot vector that indicates the label. So if the label corresponds to the class at position 3, for example, then this one hot vector is 0 everywhere except in index 3. And there, as a result, we're going to have as many blocks as the number of labels, and the size of each block is the size of phi of X. And the blocks are going to have zeros everywhere except on the block that corresponds to the third feature, where we just plug the feature vector phi of x. Okay, so by doing this, we have a perfect equivalence between these feature representations. So phi of x, we used phi of x in this talk because it's simpler and more convenient in binary classification. It's also the kind of notation that we're going to use in the next lectures when we use neural networks. But psi of x and y is actually a little bit more expressive because it allows more complex features over properties of labels. So for example, if you have labels like sports, finance, economy, and so on and so forth, we could define a class that is leisure, that includes, I don't know, sports and games, for example. And this groups 2 labels instead of 1. And you can have features that depend on either one of these 2 labels, and we could share some parameters based on that. But yeah, in the labs, I think we might need to deal with these joint features. This is why I'm talking about them here. They are still parameterized by a weight vector, but now we have 1 weighter per feature. Now, this should not be d, but d times the number of labels. And the score of a particular label is based also on a linear combination of features and their weights. But instead of writing the decision as wy times phi of x, we write it as w times psi of x and y. Okay, and if we regard this w as a vectorization of our matrix w that we had before, that contains weights for each combination of feature and class, then these 2 things are exactly equivalent. And everything still holds for all the classifiers that we learned before. So this is the difference, right? With these joint feature inputs, these joint feature mappings, our decisions look like this. With the features as we used them before, our decisions look like this. So the y is indexing the weight vector now. But apart from that, everything is really the same. Doesn't really make a big difference. All right, so there is some questions before I conclude. Okay, I see that there are several questions about joint features. So first there is a question about similarity-based methods. Since similarity-based methods still need a featurized representation of the inputs, at what point is it worthwhile to switch from a similarity-based method to a purely feature-based one? So similarity methods, theoretically, through this Mercer's theorem, they correspond to an inner product between features. But you usually use these kernel-based methods without having to work in that explicit feature space. So we work with some description of your inputs that is in your original space. You don't need to worry about this external, this corresponding feature space, which is convenient because this feature space can be very high dimensional. So it's still worthwhile to use a similarity-based method if you have a good intuition to design our similarity functions. Another question, why are we trying to predict a label using a feature we already fit the label to? Okay, so this is a good question. So these features that I was defining, the psi of x and y, the y there is not a true label, it's a hypothesized label. So we need to compute these features for all possible labels. We need to multiply it by the weights to get scores for all possible labels, and only then we make a decision. So we are feeding a candidate label to the feature, but not necessarily the true label. Then for joint features, how do we represent the data during the test time when the way label is known? I think this was the same question. So at test time, we need to represent features for all possible y's. This will give us scores for every class, and then you just do the argmax, exactly as we were doing before. If you want to compute joint features, how will these apply at test? Okay, so all questions are the same. Maybe I was not very clear in my presentation. I can show you the slide again. Let me just clean the Q&A. I can do that later. Okay, so I will show that slide in a bit. There was another question. When you make feature representation depend on labels, aren't you breaking the conditional independence assumption? So no, if we assume that the features are chosen the way I mentioned here. So if you assume that the joint features are giving zeros to all classes that are not the y that I'm computing, but all the other y's, then this is exactly equivalent to what we had before. The conditional independence assumption is stating that it's not a statement about the features, it's a statement about the probabilities, even though the features are used for mapping those things to probabilities in the naive Bayes model. And also the conditional independence assumption is only used in the naive Bayes model. It's not used in the other ones. So the conditional independence assumption is stating that features are conditionally independent given the label. And so you can still use features I was defining here. The two things are equivalent. Okay, so all the other questions are about what to do at test time. So I will just show the slide again. Let me see if I don't lose my screen this time. Okay. Okay, let me go back a few slides. So yeah, so in this case, we have two labels. The labels are location and person, and we are computing features for these two possibilities. So at test time, we could be doing this. We don't know which label is the correct one. We do this for both labels. And then our decisions are going to be assign a weight to each of these features. We are going to get a score for each possible y for each of these two classes, and you choose the class with the largest score. So it's exactly the same. We are not changing anything. If we define our features this way, this is exactly the same as we had before. It only becomes more expressive if we are doing something smarter about how to use the output label inside the feature representations. If you're doing this idea of having block vectors with zeros, then it's exactly equivalent to what we had before. Okay, so to conclude today's class, so linear classifiers are a broad class including well-known machine learning methods, includes Perceptron, naive Bayes, or Multinomial naive Bayes to be more precise, logistic regression, support vector machines. They all involve manipulating weights and features. They either lead to closed form solutions or to convex optimization problems. So we don't need to worry about local minima. This is something that we will need to worry about when we do neural networks, and we'll see that later today. Stochastic gradient descent algorithms are useful if the training data sets are large. However, linear classifiers require feature engineering, which can be painful. It's written tomorrow here, but it's actually this afternoon. In Bixia, we'll show you methods that are able to learn internal representations. So this is all for today. If there are any remaining questions, I'll be happy to take them.
Okay, I guess you answered most of the questions during the talk. So we should finish now and get back here again at 2 o'clock, okay, for the labs. Thank you very much, Andre, for the great talk. Okay.
Okay, thanks very much, and see you in a bit. Bye-bye.
See you guys later.